Welcome to Orbit Observer. It's lovely to have you here, wherever you are tonight. Maybe you're already under the blankets with the lamp turned low and the day finally letting go of you. Maybe you've got a cup of something warm cooling beside you. Or maybe you're on a train, or a long, quiet drive, or just lying in the dark, waiting for sleep to come and find you. However you got here, however the day treated you, I'm glad you came. Settle in. Get comfortable. There's nowhere we need to be for the next while except here, drifting slowly outward together. And before we begin, if you enjoy these slow journeys through the dark and you'd like more nights like this one, a gentle like and a subscribe really does help this sleepy little channel keep going. Small creators like me rely on it more than you'd think. And to everyone already here, already part of the quiet, thank you, honestly. It means a lot. So tell me, if you feel like it, where in the world are you watching from tonight? What time is it in your corner of the dark? I always like to imagine all of you scattered across the planet, all looking up at the same sky from 1,000 different windows. Now, I should warn you about something. Tonight we're going to talk about the solar system, not the version you learned in school with the 8 tidy planets in a neat little row, the real one, the crowded, strange, enormous one. And there's a chance, just a small chance, that some of it might be so strange it keeps you awake a little longer than you meant to stay. If that happens, well, at least you'll have learned something. A fair trade. But there's no need to worry about that, really. Because this is going to be slow. We're going to take our time. If you drift off somewhere in the middle, before we ever reach the cold edge of everything, that's perfectly fine. The worlds will still be here when you wake. The sun will still be burning. Nothing out there is in any hurry, and neither are we. You don't need to remember any of it. You don't need to follow every number or hold every name in your head. Just let it wash over you like a tide going out. Let the words be a sound to fall asleep to, and let the ideas drift past like lights in the dark. That's all this is meant to be. So, let's begin, shall we? I want to start with the sun, not because it's the obvious place to start, though it is, but because the sun is going to do something to your sense of scale that I think changes the whole rest of the journey. Most of us, when we picture the solar system, we picture a kind of family portrait. The sun off to one side, a bright, cheerful circle, and then the 8 planets lined up beside it, each one a respectable size, each one a member of the family. We learned them as a list. We learned a little rhyme to remember the order. And somewhere in the back of our minds, the picture settled into place. And it stayed there. And we stopped questioning it. 8 planets and a sun. That's the solar system. Here's the thing, though, that picture is almost entirely wrong. Not the facts of it. The planets are real, the order is real. But the proportions. The picture is wrong about how much of everything is actually the sun, because the sun is not one member of the family. The sun is the family. The sun contains about 99.86% of all the mass in the entire solar system. Let me say that again, slowly, because it's the kind of number that slides right past you if you're not careful. 99.86%. Almost everything that exists out here. Almost every gram of matter, every speck of rock and metal and ice and gas in this whole vast system is the sun. Think about what that means for everything else. All 8 planets, every single moon, every asteroid in the belt, every comet, every grain of dust, every frozen world out in the dark beyond Neptune that we haven't even named yet. Add all of that together, pile it all up, and it comes to about 0.14%. The leftovers, the crumbs at the bottom of the bag after the sun took its share, that's us. That's everything we've ever known, everything we've ever set foot on or sent a spacecraft toward. 0.14 of the whole. It helps sometimes to make a number like that into something you can hold. So imagine you had 1,000 grams of clay, a nice heavy lump about the weight of a bag of sugar. And imagine that lump was the entire solar system, all of it, squashed together. If you wanted to pull out the part that's the sun, you'd take almost the whole thing. You'd take 998.5 grams. And what's left, the part you'd pinch off for everything that isn't the sun, all the planets, all the moons, every last rock, would be about 1.5 grams, a pinch, a crumb you could lose between your fingers. So when we say the solar system, what we really mean, almost entirely, is the sun. Everything else is a rounding error, orbiting around it. And what a thing it is, this sun. It's a star, of course, which is easy to forget when you see it as just the warm yellow thing that makes the daytime. But that's what it is, an ordinary star, the kind astronomers file under a quiet little label called G2V. A G-type main sequence star. Don't worry about the letters. All that really means is that it's a perfectly average, middle-of-the-road star, not a giant, not a tiny ember, a steady, golden, unremarkable star, of which there are billions and billions just like it, scattered through the galaxy. The only thing that makes ours special is that it's ours. It's the one we happen to be born next to. It's old too, about 4.5 billion years old, 4.6 billion, give or take. Try to feel the size of that number for a moment, the way you'd feel the depth of dark water. 4.5 billion years. The sun has been burning steadily, patiently, since long before there was an Earth to warm, long before there was anyone here to look up at it. It has been pouring out light into the dark every second of all that time, and it'll keep going for billions of years more. On that scale, your whole life, my whole life, the entire span of human history. It's barely a flicker. A single warm afternoon in a story that goes on for ages. And it's big. I mean, truly, genuinely big in a way the words struggle with. The sun is about 1.39 million kilometers across, 1.3 million. If you tried to line up Earths across the face of the sun side by side, like beads on a string stretched across its width, you would need about 109 of them. 109 Earths just to reach from one edge of the sun to the other, and that's only across the middle. To fill the whole volume of it, you'd need over 1 million Earths poured inside like sand into a jar. Inside, down at the very heart of it, the sun is unimaginably hot. The core sits at around 15 million degrees, not 1,500, not 15,000. 15 million degrees, a furnace so deep and so fierce that it crushes the very atoms of hydrogen together and turns them into something new. And that's where all the light comes from that endless, slow crushing deep in the dark center. And by the time that energy fights its way up to the surface, the part we actually see, the part called the photosphere, it's cooled all the way down to a mere 5,500 degrees. Cooled 5,500 degrees, and we call that the cool part. That's how strange the scales get out here. So that's where we'll set our anchor for the night, the sun. 99.86% of everything. 1 million Earths could fit inside it, and it's been burning for 4.5 billion years. And it is, in the simplest possible terms, the whole show. Everything else we visit tonight, every single world, is a leftover, a crumb caught in its gravity going round and round in the dark. Now, I told you the 8-planet picture was wrong about its proportions. But here's where it gets stranger, and here's the real reason I wanted to take you on this particular journey tonight. Because it isn't just that the sun outweighs everything, it's that even within that little 1.5 grams of leftovers, even within the crumbs, the 8 planets aren't really the main event either. Let me tell you about the moons. When you think of the solar system, you think of planets. But by sheer count, the solar system isn't a place of planets. It's a place of moons. It's a place of ice. There are, as best we can count them right now, more than 290 confirmed moons orbiting through this system. Nearly 300 separate little worlds circling the planets, each one a place in its own right, with its own surface and its own story. And here's the part I love most, the part I want you to drift off thinking about. Just two of the planets, just Jupiter and Saturn. Between them, hold the overwhelming majority of all of them. Jupiter, at the last count, has around 95 confirmed moons, and Saturn has somewhere north of 146. Add those two together, just those two planets, and you get something like 241 moons, 241 little worlds kept in orbit by only two planets. Now hold that next to the headline, the 8 planets. The whole famous family we learned the rhyme for. 8. 2 planets host 241 worlds between them, and the entire roster of official planets is 8. The moons of Jupiter and Saturn alone outnumber the planets of the whole solar system by 30 to 1. More than 30 to 1. So the picture flips, doesn't it? The thing we were taught to see as the solar system, did the 8 planets in a row, turns out to be the small, bright town. And the real solar system, the actual sprawling population of it, is this enormous archipelago of moons and ice and rock, most of it dark, most of it cold, most of it circling silently far from the sun. The planets are just the few big lamps lit in the dark. The night around them is full of hundreds of other worlds.
And I should be honest with you about something, the way I'll try to be honest all night. Those numbers, 95 moons here, 146 there, they're not fixed. They're rising. Every time astronomers point a good telescope at the giant planets and look carefully, patiently, at the faint specks crawling around them, they find more. Little ones, faint ones. Moons only a few kilometers across that nobody had noticed before. The count goes up almost every year.
So when I tell you around 95 or more than 146, what I really mean is at least that many, and probably more by the time you hear this. The solar system keeps getting more crowded the more closely we look. There's something comforting in that, I think. The dark is fuller than we knew. So that's the whole shape of tonight then. We're going to leave the sun behind, the bright furnace that is almost everything, and we're going to drift outward, slowly, world by world, into the leftovers, into the 1.5 grams of crumbs. And as we go, we're going to watch the picture you grew up with come apart gently and rearrange itself into something much stranger and much bigger. Because the further from the sun we travel tonight, the more crowded and the more peculiar it's going to get. By the time we reach the cold frontier at the very end, the 8 planets are going to feel like a tiny lit village we left behind long ago, surrounded by an endless dark wilderness full of frozen worlds. That's the journey, that's where we're going. But we start close in, we start in the warm. So leave the sun behind us now, and let's drift out to the first little world circling it, the closest planet to the sun, Mercury. Mercury is small. That's the first thing to know about it, and it's a fact that's going to matter more than you'd expect. It's the smallest of the 8 planets, only about 4,879 kilometers across, and I want you to file that number away gently because it's going to come back and surprise you later tonight. Because here's the thing about Mercury, this whole planet, this full member of the planetary family. There are moons out there, not planets, just moons, circling other planets that are bigger than it. Ganymede, way out at Jupiter, is bigger than Mercury. Titan, out at Saturn, is bigger than Mercury. 2 moons, larger than an entire planet. We'll meet both of them, far out in the dark before the night is through. But hold the strangeness of that for now. A planet, smaller than a moon. The neat hierarchy you were taught, planets on top, moons beneath. It just isn't true out here. The categories blur. Some of the moons are giants, and one of the planets is a runt. Mercury has no moons of its own, by the way, none at all. It hugs so close to the sun, sitting in all that fierce gravity and heat, that it never managed to gather any little companions to circle it. It just races around the sun alone, the fastest of all the planets year after year, with no moon to keep it company in the dark. And it is a world of terrible extremes. Mercury has the largest temperature swing of any planet in the whole solar system, and the reason is a kind of cruel simplicity. It has almost no atmosphere, no real blanket of air to hold the warmth in, to spread it around, to soften the difference between day and night. On Earth, our air does that for us. It tucks us in. It carries the day's warmth into the night so we don't freeze the moment the sun goes down. Mercury has nothing like that. So on the side facing the sun, the daylight side, the surface roasts at around 430 degrees, hot enough to melt some metals. And then on the night side, with no air to hold a single scrap of that heat, the temperature falls off a cliff, all the way down to around minus 180 degrees, from 430 above to 180 below. Step from the day side to the night side, and you'd cross more than 600 degrees. The same little world, baking and freezing at once, depending only on which way it happens to be facing. And yet, and this is the thing I find genuinely wonderful about Mercury, the thing that makes it more than just a hot, dead rock, there is ice on it. Actual water ice. On the planet closest to the sun, the most sun-blasted world there is frozen water. How? How can ice survive on a world that bakes at 430 degrees? The answer is hidden quite literally in shadow. At Mercury's north and south poles there are craters, deep bowls punched into the surface long ago, and because of the particular way Mercury sits and spins, the floors of some of those polar craters never, ever see the sun, not once, not for a moment. Not. The sun stays low at the poles, and the high crater walls keep the sunlight out forever. And so down at the bottom of those craters there are pockets of permanent shadow, pools of eternal dark that have been cold for billions of years. And in that endless cold dark, water ice can sit, frozen and patient, just a short walk from one of the hottest surfaces in the solar system. We know this isn't a guess, by the way. A spacecraft called Messenger went to Mercury and it looked into those shadowed craters and it found the ice, confirmed it. Frozen water hiding in the dark on the planet that hugs the sun. I think that's one of the loveliest little facts in the whole system. That even in the harshest place there's a sheltered corner where something soft and cold can survive just by staying out of the light. So that's Mercury, a small, lonely, moonless world of brutal extremes with secret pockets of ice tucked into its shadowed poles. Let's leave it behind now and drift just a little further out from the sun to the next world along. And the next world is Venus. And Venus is going to surprise you because Venus breaks a rule you'd think the universe couldn't break. Here's the rule, the common sense one. The closer you are to a fire, the hotter you get. Mercury is closest to the sun, so Mercury should be the hottest planet. That just stands to reason, doesn't it? But it isn't true. Venus is farther from the sun than Mercury. And Venus is hotter, much hotter, the hottest planet in the entire solar system by a wide margin. The surface of Venus sits at around 465 degrees, hotter than the day side of Mercury, even though Venus is farther from the fire. So what's going on? How does a more distant planet end up hotter than the one closer in? The answer is the air. Venus is wrapped in a thick, heavy, suffocating atmosphere. And that atmosphere is mostly carbon dioxide. And carbon dioxide is very good at one particular thing. It lets sunlight in, but it won't let the heat back out. The light comes down, warms the surface, and then tries to radiate back up into space as heat. And the thick blanket of carbon dioxide catches it, holds it, traps it down near the ground like a greenhouse with the door sealed shut, like a parked car in summer with all the windows rolled up. Except on Venus, this has been running for an unimaginably long time, building and building, the heat piling up with nowhere to go until the whole planet became the oven it is now. We call it a runaway greenhouse, a warming that fed on itself until it ran completely out of control. And the end result is a surface hot enough to glow faintly, hotter than any other planet, all because of the blanket of air. And that air is heavy, crushingly heavy. The atmospheric pressure at the surface of Venus is about 92 times what we feel here on Earth. Imagine that for a moment here. The air rests on your shoulders so gently you never even notice it. There, it would press on you with the weight of deep ocean water. The kind of pressure you'd feel if you dove down hundreds of meters beneath the sea. To stand on the surface of Venus, you'd be standing under an ocean of crushing, scalding air. It's one of the least welcoming places imaginable, and it's right next door, the second planet from the Sun. Venus is moonless too, like Mercury. Just the planet alone, wrapped in its terrible heat. But the strangest thing about Venus isn't the heat or the pressure. It's the way it turns, because Venus spins backwards. Almost every world in the solar system rotates in the same direction. The direction it goes around the Sun, the way most of the spinning happened when everything first formed, but not Venus. Venus turns the other way, backwards. Retrograde is the word for it. If you could stand on its surface and somehow see through that thick, suffocating air, you'd watch the sun rise in the west and set in the east. The wrong way round entirely. And it turns so slowly, so unbelievably slowly. Venus rotates so lazily on its axis that a single day there, one full turn, takes longer than a whole year, longer than the time it takes Venus to travel all the way around the Sun. Just sit with how strange that is for a moment, the kind of strange that's nice to drift off on. On Venus, the year is shorter than the day. You could be born and grow old, and a single Venusian day still wouldn't be done turning. Time itself runs strangely there, slow and backwards under the crushing, scalded sky. So there they are, the two innermost worlds. Mercury, small and lonely and moonless, baking and freezing by turns, hiding ice in its shadows. And Venus, slow and backwards, and wrapped in a heat so total it became the hottest place of all. Two planets, neither of them with a single moon to their name, both of them harsh in opposite ways. And already, can you feel it? Already the tidy picture is bending. We were promised 8 neat planets in a row, but the closer we look, the less neat they are. One of them is smaller than a moon. One of them is hotter, farther from the fire. One of them spins backwards with a day longer than its year. And we've barely left the warmth of the sun, we've barely started. So rest here a moment. In the inner system, with the sun still bright and close behind us. We've crossed the two scorched, moonless little worlds, and ahead of us, just a little further out into the dark, there's a pale blue one waiting. A world with a single, unusually large moon, and the only place we've ever found that's soft enough and wet enough and warm enough for anything at all to live. But we'll come to that next. There's no rush. The road outward is long, and it only gets stranger from here, and we'll take every step of it slowly. Now, before we drift any further, let me say a quiet thank you to everyone already settled in here with me tonight. If these slow journeys help you wind down, a gentle like and a subscribe really do help this little channel keep going. Small creators like me lean on that more than you'd think. And while you're getting comfortable, I'd love to know, where in the world are you watching from tonight? What time is it in your corner of the dark? There's something lovely about imagining all of us scattered across the globe, lying still and looking up at the same handful of worlds. But back to that pale blue one ahead of us, Earth, our own world, the third stone out from the sun. We won't dwell too long on home because you already live there, and tonight we're trying to leave it for a while. But it's worth pausing on one thing as we pass. Earth has a single moon, just one, and yet that moon is unusual. It's the 5th largest moon in the entire solar system, and it's enormous compared to the planet it circles, about a quarter of Earth's own diameter. Most moons are tiny chips next to their worlds. Ours is almost a companion, a near twin riding along beside us, close enough to pull the oceans into tides. Hold on to that for later, that idea of a moon so large it almost makes a pair. We'll meet a stranger version of it much, much further out, at the cold edge of everything. And here's a thought to drift on. Earth is, so far, the only world we've ever found with liquid water sitting right on its surface, and the only place we've ever found life of any kind. The whole vast tour we're taking tonight, hundreds of worlds, billions of frozen rocks, and only this one small blue marble has ever woken up. That's not a sad thought. It's a soft one. You happen to be lying on the single living world we know of in the whole, leftover, 14%, a small, warm exception in a very large quiet. But we're moving outward, and the next step takes us somewhere colder and redder. Mars. The 4th planet, rust-colored and dry, the one we keep dreaming about visiting. And here, finally, after 2 moonless little worlds and our own single large moon, we find something new. Mars has moons, 2 of them. But don't picture anything grand. They're tiny, lumpy, potato-shaped things, more like captured boulders than proper worlds. Phobos and Deimos, their names borrowed from the old Greek words for fear and dread, the companions of the god of war, fitting names for the moons of the red planet, even if the moons themselves are about as frightening as a couple of drifting pebbles. These 2 probably weren't born alongside Mars at all. The best guess is that they're captured asteroids, or maybe leftover rubble, that wandered too close and got snared by the planet's gravity. And there's something quietly poignant about the larger one, Phobos. It's slowly spiraling inward, drawing a little closer to Mars with every slow circle, and in something like 50 million years, it will either be torn apart by the planet's pull or come crashing down. 50 million years is an unimaginable stretch of time to us. Longer than there have been people, longer than there have been most of the animals you know. And still, on the clock of the solar system, that moon is falling. Nothing out here is truly permanent. Even the moons are on their way somewhere, just very, very slowly. Mars keeps a couple of other records too, and they're worth carrying off to sleep, because they're the kind of thing that sounds made up and isn't. There's a mountain on Mars called Olympus Mons, a vast old volcano, and it stands about 22 kilometers high. That's nearly 3 times the height of Everest, on a planet smaller than our own. And there's a canyon there called Valles Marineris, a great gash in the surface that runs for roughly 4,000 kilometers. If you set it down on Earth, it would stretch most of the way across an entire continent, a canyon you could lose whole countries in on a cold red world with 2 little falling moons. Picture it, if you like, the tallest mountain and the longest canyon we know of, sitting silent in the dark, with no one there to see them but a few of our small, wandering robots. And then just past Mars, the tidy picture of the solar system breaks open completely, because between Mars and the next planet there isn't a planet at all. There's a gap, a wide, dark gap, and floating in it, millions of bodies. This is the asteroid belt, and it's one of the most misunderstood places in the whole system. If you've ever seen a film where a brave little ship has to dodge and weave through a thick storm of tumbling rocks, hold that image gently and then let it go, because the real asteroid belt is almost nothing like that. Yes, there are millions of objects out there, scattered between Mars and Jupiter. That part is true, but the belt is mostly empty. Empty in a way that's hard to hold in your head. The rocks are so spread out with such enormous stretches of nothing between them that if you were actually flying through it, you might never see a single one with your own eyes. Every spacecraft we've ever sent outward has passed straight through this belt without trouble, without a single careful bit of dodging. It's less a wall of stone and more a vast, thinly scattered sprinkling of grit across an ocean of dark. And here's the fact that really puts it in place, the one to drift off on. If you gathered up every single object in the entire asteroid belt, every rock and boulder and mountain-sized chunk, millions upon millions of them, and squeezed them all together into one ball, that ball would still only weigh about 3% of our moon. 3%. All those millions of bodies, all that talk of a great rocky river between the planets, and together they don't even add up to a small fraction of the single moon hanging over your roof tonight. The belt is mostly the gap, mostly the quiet. One body in that belt is large enough to be different from the rest. Its name is Ceres, and it holds about a third of the belt's entire mass all by itself. One round little world doing the work of countless scattered rocks. Ceres is big enough and round enough that it gets its own special title. It's called a dwarf planet, the only one we'll find this close to the Sun. Tuck that phrase away, dwarf planet, because we are going to meet a whole crowd of them later, out in the cold, far past the planets you learned to name. There's another world in the belt worth a passing nod to, called Vesta, the second largest and the brightest of all the asteroids, the only one that ever drifts close enough and bright enough to be glimpsed with the naked eye on a dark night. But it's Ceres, that small round dwarf among the rubble, that's the real signpost here.
A hint of stranger things to come, so look back just for a moment at how far the tidy picture has bent. We started with the Sun, almost all the mass there is, and a promise of 8 neat planets. And one by one the neatness has fallen away. A planet smaller than a moon. A planet hotter the farther it sits from the fire, turning slowly backwards. Our own world, the single living one with its strangely oversized moon. A red planet with 2 little captured moons, one of them quietly falling.
And now a wide gap full of millions of rocks that somehow add up to almost nothing, with a small, round dwarf hidden in the middle of it. We are only halfway to the first of the truly giant worlds, and already the map you carry in your head is coming loose at the edges, because we are about to cross from the inner system into the outer, from the realm of small rocky worlds into the realm of the giants. And it's out there, just beyond this empty belt, that the real surprise of tonight's journey is waiting. Out there, 2 enormous planets are about to come into view, and around them, swarming in the dark, are more worlds than all 8 planets put together. Hundreds of moons, some of them larger than Mercury, some of them hiding oceans, one of them raining liquid fuel into seas. The leftover 0.14% is about to get very, very crowded, but not yet. For now, just rest here on the threshold with the inner planets behind us and the long, cold dark ahead. We've come a good way already, past the scorched and the frozen and the rusted and the empty. And there's no need to hurry over the gap. The giants will still be there. They've been there for over 4 billion years, patient and slow, and they can wait a little longer while you settle deeper into the quiet. So let us begin the crossing. The asteroid belt is behind us now, that vast ring of rubble and silence, and we are moving outward into the cooler dark. But before we left the inner system entirely, we passed something I want to stay with for just a moment longer. Something easy to take for granted because it is home, and because home tends to blur into background when you have been staring at it all your life. Earth. Third rock from the sun, as the saying goes, 1 AU out. A distance so comfortable, so precisely suited to liquid water on a surface, that for a long time people imagined it must have been designed that way. The oceans alone cover about 70% of the surface. There are forests and ice caps and weather systems that spiral for hundreds of kilometers. There is the sound of rain and the smell of it. There is life in every crevice and current and column of air, in forms so varied they still haven't all been named. And in the middle of all of this, wrapped in its familiar blue haze, the pale lights of cities glowing on the night side, Earth is the only world in the entire solar system, across everything we visited and everything we know, where any of that is happening. One world, out of somewhere around 290 confirmed moons, 8 planets, 5 recognized dwarf planets, millions of asteroids, and all the unknown billions of cold bodies in the dark beyond. Just one. That is worth holding quietly for a moment. That is the kind of thought that tends to slip in during the last minutes before sleep, the kind of thought that is either terrifying or wonderful, depending on how you're feeling. Tonight, let's let it be wonderful. And yet, even as we linger on Earth's peculiar loneliness, there is something else about this world that deserves attention, something overhead that most people barely notice because it has always been there, hanging in the sky like furniture. The moon. The moon is not, by any reasonable measure, what you'd expect a moon to be. Most moons in the solar system are small compared to the world they orbit. They are captured rocks, little irregular shapes tumbling in low orbit, the kind of thing you'd barely notice on a photograph of the planet itself. The moons of Mars are like that. Many of Jupiter's outer moons are like that. Even several of Saturn's are, in planetary terms, tiny. The moon is not tiny. The moon is about 1/4 of Earth's own diameter. If you set the moon beside Earth in a diagram to scale, you would see not a planet with a distant speck of a companion, but something closer to a double world. 2 bodies, admittedly very different in size, but both clearly substantial, turning around each other as they travel together. And in terms of rank, the moon sits 5th among all the moons in the solar system, 5th largest out of nearly 300. That is an extraordinary position for the companion of a relatively small rocky planet. The question of why the moon is so large relative to Earth. Why, when we look around at other rocky planets and find Mars's 2 captured pebbles, and Venus with nothing at all and Mercury with nothing at all, is a question that scientists have puzzled over for a very long time. The leading answer, and it is a dramatic one, is that something very large hit the young Earth billions of years ago, when the solar system was still being assembled and the inner planets were still being battered by debris from all directions. Something roughly the size of Mars, a planetary embryo moving at an angle, striking a glancing blow. The collision threw an enormous spray of material into orbit around Earth, rock and vapor, and the mantle of the impactor. And over time, that material coalesced into the moon. This is called the giant impact hypothesis, and while it remains a hypothesis, it is well supported and widely accepted. It explains the moon's size, it explains why the moon's composition is similar to Earth's outer layers, it explains the Earth-Moon system's unusual angular momentum, and it explains in a quiet way something else, that Earth itself might not have been quite the same world without it. The moon's gravitational pull stabilizes Earth's axial tilt over geological time, keeping the seasons from wandering into extremes. It drives the tides that slosh through the oceans, and for billions of years it has kept a familiar, constant face turned toward us. The same face, always, because the Moon's rotation has been locked to its orbit by gravitational friction over deep time. We have never seen the far side with the naked eye, not once in all of human history until spacecraft first flew around and looked. The Moon, fifth largest moon in the solar system, 1/4 of Earth's width, and the only body beyond Earth that human beings have ever stood on. 12 people walked on the Moon. Between 1969 and 1972, the last of them, Eugene Cernan, lifted his boot from the lunar surface in December of 1972, and no human has been back since. The footprints are still there, precisely because there is no wind on the Moon, no weather, no erosion, only the very slow sandblasting of micrometeorite impacts over millions of years. The footprints will last, in recognizable form, for something on the order of millions of years. That is a fact that tends to arrive quietly and then keep expanding. And now we move on. Earth recedes behind us. The next world outward, ruddy, cold, thin-aired Mars, comes into focus. Mars is a desert. A true desert, not in the way we use the word for the driest places on Earth, but a world where the average surface temperature is around -60 degrees Celsius, where the air pressure is less than 1% of Earth's, where the air itself is almost entirely carbon dioxide, and where liquid water cannot survive at the surface under those conditions. Whatever rivers carved the ancient valley networks visible in photographs of Mars today, whatever ocean may have lapped at the ancient northern lowlands, all of it is long gone. What remains is iron oxide dust, a pink-orange sky, wind, and silence. And 2 moons. The moons of Mars are named Phobos and Deimos, fear and dread, the 2 attendants of the god of war in Greek mythology. They are small and dark and not particularly round. Phobos, the inner one, is only about 22 kilometers across. Deimos is smaller still, about 12 kilometers. Neither would look like much more than a large irregular rock if you saw them photographed alone, without scale to reference. They do not shine with the reflected brilliance of the Moon in our sky. From the surface of Mars, Phobos would appear as a bright point of light, noticeably larger than the other stars, rising and setting twice in a single Martian day. Deimos, farther out, would be almost indistinguishable from a bright star. They are almost certainly not original to Mars. The leading explanation, and it is the more intuitive of the two because it fits their irregular shapes and their dark, carbon-rich composition, is that they are captured asteroids, or possibly debris from a very early collision dragged in from the asteroid belt by Mars's gravity at some point in the distant past. We don't know exactly when or how, but they move in orbits that suggest they haven't been there forever, and Phobos in particular is not going to be there much longer. Not on the geological timescale. Phobos orbits Mars so close, closer to its planet than any other moon in the solar system to its, that it actually completes its orbit faster than Mars rotates. Seen from the Martian surface, it rises in the west and sets in the east, the reverse of how the Sun moves, lapping the whole planet several times a day. And with each orbit, tidal forces between Phobos and Mars steal a tiny fraction of orbital energy, pulling the Moon very slightly inward. The numbers have been worked out carefully. Phobos is spiraling toward Mars at a rate of about 1.5 centimeters per year. In roughly 50 million years, it will pass so close to Mars that the planet's tidal forces will tear it apart, or it will fall inward and crash. Either way, Mars's largest moon will be gone, replaced perhaps by a thin ring of debris or a scattered trail of craters across the Martian surface. 50 million years is a very long time, but compared to the 4.5 billion year age of the solar system, it is a recent afternoon. Phobos has already been orbiting for billions of years, and it has perhaps 50 million left. We have caught it, in astronomical terms, near the very end of its story. Deimos, by contrast, orbits farther out beyond the distance where tidal friction slows it and is gradually drifting away, much more slowly and much more gently than Phobos is falling in. Mars is losing both moons, one by catastrophe and one by slow departure, but not tonight and not for a very long time. Now, before we leave Mars, because it would be a genuine shame to pass it without pausing, Mars is not just a cold desert, it is a cold desert with the most extreme geography in the solar system. There is a volcano on Mars called Olympus Mons. You have probably heard the name, but let me try to give you a sense of the scale, because the number alone tends not to land the way it should. Olympus Mons stands approximately 22 kilometers above the surrounding plain. That is roughly 2.5 times the height of Mount Everest, measured from base to summit. The base of the volcano covers an area roughly the size of France. If you were standing at the outer edge of its base and looking toward the summit, you would not see it. The volcano is so wide that its peak lies beyond the horizon, curved away behind the curvature of Mars itself. From the summit, looking outward across the caldera, a depression at the top large enough to hold several major cities, you would not feel like you were on a mountain at all. The slope is so gradual, rising so gently over such an enormous distance that the terrain would feel almost flat. And yet, you would be standing 22 kilometers above the plain. The largest known volcano in the solar system, and one whose existence implies a past of extraordinary geological violence, of heat rising from a planetary interior through the same spot again and again, building and building over hundreds of millions of years, because Mars, unlike Earth, has no moving tectonic plates to carry the crust away from a hot spot. And then there is Valles Marineris, the canyon system, named after the Mariner 9 spacecraft which first revealed it in detail. Valles Marineris runs for approximately 4,000 kilometers along the Martian equator. That is roughly the width of the continental United States. At its widest, it stretches about 200 kilometers across. At its deepest, it plunges 7 or 8 kilometers below the surrounding plateau. The Grand Canyon of Earth, one of our most dramatic geological features, is about 446 kilometers long, 16 kilometers wide at its broadest, and about 1.5 kilometers deep. Valles Marineris makes it look like a small garden ditch. If you placed Valles Marineris over a map of Europe, it would stretch from the western coast of Portugal to the border of Iran. This is Mars, not just a dusty world with a thin atmosphere and a pink sky, but a world of extraordinary, almost incomprehensible scale in its landforms. As if the geology that Earth expresses through many different places and processes all got concentrated and amplified on this one cold, quiet world. And then Mars becomes quiet behind us and the gap opens up. The gap between Mars and Jupiter is not nothing. It is where the asteroid belt lives, and we drifted through the edges of it on our way here. So let me spend a little time with what it actually is, because what it actually is turns out to be one of the great surprise reversals of the solar system. In the popular imagination, in science fiction films, in the image you probably grew up with, the asteroid belt is a dense, dangerous field of tumbling rocks that spacecraft have to navigate carefully, weaving between close-packed boulders. This image is so widespread and so vivid that it feels like knowledge. It feels like something you were told. And in a very loose sense, there is truth in it. There are millions, possibly hundreds of millions, of rocky and metallic objects in the asteroid belt, ranging from tiny pebbles to the dwarf planet Ceres. The belt is real, the rocks are real, but the density, the idea that it is crowded, that part is mythology. The asteroid belt is overwhelmingly empty. If you were to fly a spacecraft through it, which we have multiple times, including the Galileo probe on its way to Jupiter and the New Horizons probe on its way to Pluto, the statistical probability of randomly striking an asteroid is vanishingly small. The objects in the belt are separated from each other, on average, by hundreds of thousands of kilometers. Space probes don't have to dodge them. They fly straight through, and they have to deliberately aim to encounter one if they want a close look. Every close-up image we have of an asteroid has required a deliberate course correction to get near it.
And the mass. This is the real surprise. You might expect that with millions upon millions of objects, the belt's total mass would be substantial. It is not. All of the material in the asteroid belt, all of those millions of rocks and pebbles and boulders, and the dwarf planet at the center of it, adds up to only about 3% of the mass of our moon. 3%.
The moon, that small companion overhead that you barely think about, outweighs the entire asteroid belt by a factor of more than 30. Where did the rest of the mass go? Why is the asteroid belt so thin, so sparse, so strangely underpopulated given how many billions of years it has had to accumulate material? The answer is standing just beyond the far edge of it, enormous and patient and gravitationally overwhelming. Jupiter. Jupiter's gravity, even from the far side of the belt, is so powerful that it continuously stirred and disrupted the material in that region. It prevented the rocky bodies there from coalescing into a planet. Wherever a nascent protoplanet might have begun to grow, Jupiter's tidal pull perturbed the orbits of nearby bodies, sending collisions at velocities too high for accretion, flinging material out of the belt entirely, herding some of it toward the Sun and some of it out into the far solar system. Jupiter essentially robbed the asteroid belt of its right to become a fifth rocky planet. The material that didn't fall into the Sun or get ejected is what remains, the ghost of a world that never formed, spread out across the width of the inner solar system's outer edge. And the series we have now. The largest object in the asteroid belt, a roughly spherical body about 945 kilometers across, large enough to have pulled itself into a somewhat round shape under its own gravity, which is why it qualifies as a dwarf planet, holds about a third of the belt's total mass all by itself. One object, in the middle of millions, holds a third of the region's entire mass. Around it, the smaller stuff thins and spreads in every direction. Ceres is thought to be old and cold and icy beneath its surface, and there are hints, from the Dawn spacecraft, which orbited it for several years, of briny water, possibly even a thin brine layer not far below the crust. Strange bright spots in one of its craters turned out to be deposits of sodium carbonate, likely left by water that once reached the surface and evaporated. A world in the middle of the belt, quietly preserving some of the most ancient, water-rich material in the solar system. Then there is Vesta. Second largest object in the belt, not quite round enough to qualify as a dwarf planet, but massive enough and bright enough to be, on rare occasions, just barely visible to the naked eye from Earth under perfect conditions. The only asteroid that can claim that distinction. Vesta has been battered hard. There is a crater near its south pole named Rhea Silvia, so large that the impact that created it would have been catastrophic, blasting material off the surface in all directions. Some of that material became meteorites, which have since fallen to Earth. Vesta pieces, identifiable by their distinctive mineralogy, are sitting in museum collections on our planet right now. But Ceres and Vesta, fascinating as they are way stations, not the destination tonight. Jupiter is the destination, and Jupiter is not a planet in the usual sense of the word. Or rather, it is, technically. But what that word encompasses in Jupiter's case is something so much larger and stranger than the rocky planets of the inner system that the same word barely fits. Jupiter is a world, but it is also a system, almost a small solar system in its own right, with a hierarchy of orbiting bodies and a gravitational reach that shapes the entire solar system around it. Let's start with the body itself. Jupiter is a sphere of mostly hydrogen and helium. There is no surface to stand on. Beneath the thick cloud layers, which are themselves thousands of kilometers deep, the gas gradually becomes denser and hotter, the hydrogen compressing under the weight of everything above it into forms of matter that don't exist naturally anywhere on Earth. First, a very dense gas, then something called metallic hydrogen, a state where electrons move freely through the hydrogen the way they do in a metal, conducting electricity, generating a magnetic field so vast it extends farther than the planet Saturn. If you could see Jupiter's magnetic field, it would be larger in our sky than the full moon. The cloud tops are where the visible features live, the stripes, the bands of lighter and darker material, the turbulence and storms that race around the planet at enormous speeds. And the most famous feature of all, the Great Red Spot, an ancient storm, wider than the entire Earth, that has been spinning in the Jovian atmosphere for at least 3 or 4 centuries. It was first noted in detail by astronomers in the 17th century. It has been there ever since. The storm itself has been slowly shrinking over the decades of careful modern observation, which raises the question of whether it might eventually dissipate. But for now, it is still there, an anticyclone, a hurricane-like system rotating in the opposite direction to the storms around it, colored that distinctive brick red by chemical compounds whose exact composition we still don't fully understand. A storm larger than Earth, centuries old, still going. And this, immense as it is not the reason Jupiter commands our attention tonight. The reason is the moons. As of the best current counts, Jupiter has 95 confirmed moons. 95. That number has changed over the decades and is likely to change again as surveys improve and smaller, fainter objects are detected. But 95 is where things stand as of the most recent confirmation, and it is almost certainly not the final number. Most of those moons are small and distant and dark, irregular chunks of rock and ice captured long ago by Jupiter's enormous gravity, tumbling in elliptical orbits that are inclined and eccentric, nothing like the neat circles of the inner system. Many of them are probably fragments of larger bodies that were torn apart, or captured asteroids from the outer belt. But then there are the four that Galileo Galilei saw in the first weeks of January 1610, when he turned his newly improved telescope toward Jupiter and noticed 4 small points of light arranged in a line beside the planet. He watched them night after night and realized they were moving, not moving the way background stars would as Earth shifted its position, but moving in a way that made sense only if they were orbiting Jupiter. He saw them change their arrangement, one sliding to the other side of the planet, another disappearing behind it and reappearing. He understood what he was looking at, worlds in orbit around another world, not around Earth, not around the Sun, around Jupiter. This was, in 1610, a genuinely radical observation. It was one of the pieces of evidence that helped dismantle the idea of Earth as the center of all celestial motion. These 4 moons are called the Galilean moons after their discoverer, though they also carry older names: Io, Europa, Ganymede, and Callisto. And they are not small and dark and irregular. They are worlds. Io is the innermost. It orbits Jupiter at about 420,000 kilometers, closer to Jupiter than our moon is to Earth. And the gravitational interaction at that distance between Io and the enormous mass of Jupiter pulling on one side and the other Galilean moons pulling in a gravitational rhythm from outside creates something extraordinary: tidal flexing. Jupiter's gravity stretches Io toward it. As Io orbits, this stretching flexes and relaxes in the interior, generating heat through friction, and the same principle that warms your hands when you rub them together, but operating through an entire world. The result is that Io is the most volcanically active body in the solar system. Not once upon a time volcanic, not arguably volcanic, but actively, continuously, dramatically volcanic right now. Io has hundreds of active volcanoes. When the Voyager 1 spacecraft flew past in 1979, scientists were expecting to see something like a cratered moon, battered but geologically quiet. What they saw instead was a world with surfaces of vivid yellow and orange and white and red, colored by sulfur and sulfur dioxide in various forms, and at least one visible volcanic plume erupting from the surface into space as Voyager watched. It was the first time active volcanism had been seen on another body. The Galileo spacecraft arriving in the 1990s confirmed the extraordinary extent of it: lava lakes, volcanic mountains, calderas. And then Juno, currently orbiting Jupiter and making periodic close flybys of Io, has sent back recent images of eruptions ongoing, geysers of molten silicate rock that dwarf anything we have on Earth. The surface of Io is probably one of the most geologically violent places in the solar system. It is constantly being repaved by lava flows, which is why it has very few impact craters. The craters fill in almost as fast as they form. Io is a world in perpetual renewal, tortured and remade continuously by the invisible grip of Jupiter's tidal hand. Next outward from Io is Europa, and Europa is, in its own quiet way, perhaps the most important world in the solar system besides our own. Europa is smaller than Io, about the size of our moon, roughly 3,100 kilometers in diameter. From a distance, it looks almost featureless, a pale, smooth, whitish sphere, crisscrossed by long, dark lines that seem to trace across it like cracks in an eggshell, and that is almost exactly what they are. Europa is covered in a shell of water ice. Beneath that ice, kept liquid by the same tidal heating that drives Io's volcanoes, though less extreme because Europa is slightly farther from Jupiter, there is very likely an ocean. A global ocean of liquid salt water wrapped entirely around the interior of the world beneath its frozen skin. The evidence for this ocean is strong and has been building for decades. The pattern of those cracks in the ice surface suggests a layer underneath that moves and flexes. Measurements of Europa's magnetic field suggest an electrically conducting fluid, something like a salty ocean, exists beneath the ice, influencing the field in ways that a solid interior would not. More recently, hints of water vapor have been detected above the surface, possibly from plumes or leakage through the cracks. And the estimates for the volume of water involved are staggering. Europa's ocean, if it exists as current evidence suggests, may contain more liquid water than all of Earth's oceans combined. Beneath a few kilometers to a few tens of kilometers of ice, we're not sure exactly how thick, there may be a global saltwater ocean, perhaps 100 kilometers deep, and where there is water and heat and chemistry, where these things come together, the question of life becomes at least worth asking. Not certain, not even probable necessarily, but worth asking. The environments that might exist at the bottom of Europa's ocean, where the water meets a rocky seafloor, where hydrothermal vents might exist powered by tidal heat, where mineral-rich water circulates, bear some resemblance to environments on Earth where life is found in abundance, in the deep ocean, far from sunlight, thriving on chemical energy alone. Europa is, because of all of this, one of the primary targets of ongoing and future exploration. NASA's Europa Clipper spacecraft, currently en route, will make dozens of close flybys of Europa to study its ice shell and ocean in unprecedented detail. And then there is Ganymede, the largest moon in the solar system, larger than Mercury, larger than Pluto, a world in its own right, 764 kilometers wider than Mercury, though less dense and therefore less massive. Ganymede is an ice and rock world layered like Earth, a metallic iron core, a rocky mantle, an icy outer layer. And it has something no other moon in the solar system is known to have, its own magnetic field. Generated by its iron core, the way Earth's magnetic field is generated by ours, Ganymede's magnetic field carves out a small bubble of magnetosphere inside Jupiter's far larger one, creating aurora at Ganymede's poles. The Hubble Space Telescope has observed these aurora and their subtle movements as Jupiter's magnetic field rocks Ganymede's have been used to further confirm the presence of a subsurface saltwater ocean beneath Ganymede's ice, a second ocean moon at Jupiter. The ESA's JUICE mission, Jupiter Icy Moons Explorer, launched in 2023 and is on its way to the Jovian system, with Ganymede as its primary destination. Then Callisto, the outermost of the four. Callisto is roughly the same size as Mercury, about 4,800 kilometres across, and it is one of the most heavily cratered surfaces we have seen in the solar system. Unlike Io, which is being continuously repaved, and unlike Europa and Ganymede, whose surfaces show evidence of geological activity, Callisto's surface appears to have been essentially unchanged for 4 billion years. It is like a geological museum, a record of the early solar system's violent bombardment period, preserved in ice and rock without modification. Every crater you see on Callisto is ancient. The surface you're looking at when you photograph it is the surface of a world that has been largely untouched since shortly after its formation. Callisto may also have a subsurface ocean suggested by magnetic field measurements, though the evidence is less clear than for Europa or Ganymede. 4 worlds, 4 moons discovered in 1610 by a man with a handmade telescope. Io, violently volcanic. Europa, possibly harboring an ocean larger than all of Earth's. Ganymede, the largest moon in the solar system, with its own magnetic field. Callisto, a crater-scarred time capsule from the early solar system. Any one of them placed in another solar system orbiting another star would be considered a remarkable discovery. Here at Jupiter there are 4 of them, and they are orbited by 91 additional moons whose names you'd have to consult a catalogue to find. Jupiter is not just a planet. Jupiter is a world system, a system within a system, and it contains more confirmed moons than any other planet in the solar system, at least as of now, with the count almost certainly still rising as our detection methods improve and our survey telescopes peer deeper into the dark around it. But Jupiter is not alone in this. There is another planet just a little farther out that has been giving Jupiter a run for its count, and as of very recently has actually taken the lead. We are not quite there yet. There is the ring after all. Jupiter has rings too, thin and dusty ones, barely visible compared to what comes next. There is the immensity of Jupiter's magnetosphere, stretching so far that if it were visible from Earth, it would appear larger than the moon in the sky. There is the fact that Jupiter alone, among everything in the solar system that is not the Sun, holds roughly 2/3 of all the mass of everything that is not the Sun. Think about that for a moment. 2/3 of the mass of everything, every planet, every moon, every asteroid, every comet, every piece of Kuiper Belt ice, everything is inside Jupiter. The other 6 planets and all their moons and all the belts and all the scattered disk objects share the remaining third. Jupiter doesn't just dominate the outer solar system. Jupiter is the outer solar system in terms of sheer gravitational weight. And yet, for all its mass, for all its moons, for all its storms and its magnetic empire, Jupiter is not the planet that will most arrest us when we continue outward. Because just beyond Jupiter, at roughly 9.5 astronomical units from the Sun, 9.5 times the Earth-Sun distance, there is something waiting that of all the sights in the solar system might be the one most worth lying still and simply imagining. We are not rushing toward it. There is still the gap between Jupiter and Saturn, a wide belt of space, cold and quiet, where the asteroid belt's distant cousins sometimes wander, and where the occasional comet drifts on its long ellipse. We have time to let the image of Jupiter's 4 great moons settle, to think about Io pouring lava into space, and Europa hiding its cold, dark ocean, and Ganymede with its own aurora dancing in the Jovian sky, and Callisto lying there unchanged for 4 billion years, patient and pockmarked and ancient. Somewhere in the outer dark ahead of us, a ringed world is waiting. Its moons are even more numerous. Its largest moon is even stranger than anything at Jupiter, and one of its small icy moons is doing something that should not, by any ordinary measure, be possible. It is spraying an ocean into space. But for now, we rest here, in the long distance between the giants, with 95 moons behind us in orbit around Jupiter alone. 95 confirmed worlds, each one a place, each one with its own character and its own story and its own kind of silence or fire or ice, and all of them together still only a fraction of what the total count across the whole solar system has become. We began tonight's journey at 8 planets. That number has not changed officially, but the solar system beneath it, the real population, the one that doesn't fit on the poster you had on your wall as a child, is already, even this far out, approaching 100 moons for Jupiter alone, with one more enormous world still to come. And beyond that, the belt of ice that stretches from 30 to 50 AU, and the dwarf planets, and the scattered disk, and the objects with names that most people will never hear. The 8 planets are not the solar system. They are the lobby. And the lobby behind us, with its rocky worlds and its captured moons, and its stolen birthright of a 5th planet turned instead into a thin, empty belt, already gives way to something so much vaster and stranger that the words are almost insufficient. Almost. So we keep going. Slowly, because there is no hurry out here, and the dark between the giants is wide and still, and the kind of quiet that you can let yourself fall into if you want to. Let Jupiter recede into the black behind us, its cloud bands slowly thinning as distance takes it, its Galilean moons becoming first small points of light and then simply part of the darkness around it. Let the great red spot fade, that centuries-old storm, that hurricane wider than Earth. Let the magnetic empire of Jupiter stretch out behind us, vast and invisible. Ahead, barely visible yet at this distance, there is a faint brightening, a pale, ringed light. The planet with the most moons in the solar system, the planet where geysers of water rise from tiny worlds and fall back as rings, the planet whose largest moon is more like a planet than a moon by almost every measure, except the accident of what it orbits. We are not there yet. Let the distance come slowly. Let the image of Jupiter's 4 great worlds hold in mind for a while longer. Io burning, Europa hiding its sea, Ganymede with its magnetic crown, Callisto dreaming in its ancient craters, and let the dark between the giants be what it is. A long, cold, beautiful nothing that exists at a scale almost too large for the mind to hold without slipping towards sleep, which is perfectly fine. The solar system will still be there in the morning. It has been there for 4.5 billion years, and it is patient with human attention spans in a way that the universe perhaps has always been. And then gradually the pale brightening resolves, it sharpens, it takes on its extraordinary shape, Saturn. Even before you reach it, even at the distance where it is still just a brightening smear in the dark, you can see that something is different. Something is wrong. In the most beautiful possible sense of the word, wrong. No other planet looks like this. No other thing in the solar system looks like this. Jupiter is enormous and banded and alive with color, but it is essentially a sphere. Saturn is a sphere wearing a hat, a sphere with wings, a sphere that looks, when you first see it properly, like someone has drawn a planet in a child's sketchbook and then couldn't quite believe what they'd made. But we are getting slightly ahead of ourselves. Before Saturn, there is still work to do in Jupiter's neighborhood. 3 of the 4 Galilean worlds are still waiting for their full moment. You remember Io, we touched on it before, that first world out from Jupiter, the one that burns. But let us settle here a moment because Io deserves more than a single sentence. Io is the most volcanically active body in the entire solar system. Not just active, not just geologically lively, it is the most violent place we know of anywhere. When the Galileo spacecraft arrived in the 1990s and began sending back images, and later, when the Juno mission added to that picture, what scientists saw was a world that is essentially turning itself inside out on a continuous basis. Hundreds of active volcanoes, hundreds.
Not dormant, not ancient. Active, right now, erupting, some of them continuously for as long as we have been watching. Lava lakes that sit open and glowing at the surface. Volcanic plumes that rise hundreds of kilometers into space, spreading sulfur and sulfur dioxide across the face of this little moon like a bruise that keeps refreshing itself.
Io is roughly the same size as Earth's moon. And yet where our moon is the quietest geological body you could imagine, a cold, crater-pocked, nearly changeless landscape, Io is the opposite. Our moon has been geologically dead for billions of years. Io looks like it might be the most alive solid body in the solar system. Why? Why is a moon of Jupiter in this state when our own moon, at a similar size, is frozen into silence? The answer is Jupiter itself. That immense gravitational field we talked about, the same field that captured so many moons, that cleared the asteroid belt, that shaped so much of the solar system's architecture, does something very specific to Io. It squeezes it. The other large Galilean moons, Europa and Ganymede in particular, also pull on Io gravitationally, and the combined effect is to continuously flex and stretch Io's interior, like squeezing a rubber ball that never gets the chance to rest. That squeezing generates heat. Enormous, relentless heat. Heat that melts rock and keeps it molten and forces it to the surface again and again and again. We call this tidal heating, and Io is the solar system's most extreme example of it. There is something almost hypnotic about Io when you look at images of it. Its surface is painted in yellows and oranges and whites, sulfur in its various forms, laid down over and over in fresh coats as eruptions come and go. Where the moon is grey and timeless, Io is vivid and constantly rewriting itself. If you came back to Io in 100 years and compared the surface to an image taken today, it would look different. Things would have moved. New flows would have covered old ones. Whole features would be gone. Io cannot rest. Jupiter will not let it. And here is a small thing to hold in mind as you drift: that violence, that relentless geological churning, that fire. It is happening right now. While you are lying wherever you are lying, while the room is quiet and the world outside has gone still, somewhere in the outer solar system, a world the size of our moon is erupting. Continuously, it has been erupting all night. It will be erupting all tomorrow. It erupted throughout all of last century and the century before that, and far back before any human being had any idea it existed. The solar system does not wait for us to look. From Io, we drift inward just slightly. No, not inward toward Jupiter, but to the next moon out, the second Galilean world, the one that of all the moons in the solar system perhaps carries the most weight in terms of what it might mean for us, for the question of whether we are alone. Europa. Europa is smaller than our moon. Its surface from above looks almost clean, smoother than any other solid body we know of, and that smoothness is the first clue to what is happening underneath. There are almost no impact craters on Europa, which is strange because in 4.5 billion years, a small world should accumulate craters the way a neglected car accumulates dents. The absence of craters means the surface is young, geologically young, which means something is renewing it. Something is erasing the old scars and laying down fresh ice. The surface of Europa is water ice. Beneath that ice, and this is where astronomers use phrases like strongly inferred and consistent with all available evidence, is an ocean of liquid salt water. A global ocean completely enclosing the interior, kept liquid by the same kind of tidal heating from Jupiter that drives Io's volcanoes, but gentler here, enough to warm from below without the catastrophic surface expression Io experiences. The ocean is not shallow. Current estimates suggest it could be 80 to 170 kilometers deep. For comparison, the average depth of Earth's oceans is about 3.5 kilometers. Europa's hidden ocean is thought to be somewhere between 2 and 5 times as deep, and it covers the entire world beneath the ice. And here is the number that tends to stop people. The total volume of water in Europa's subsurface ocean is estimated to be roughly 2 to 3 times the volume of all Earth's oceans combined. Our oceans cover 70% of our planet's surface and reach their deepest points at nearly 11 kilometers. Europa's ocean, invisible from space, sealed under ice, orbiting a gas giant 500 million kilometers from the Sun, may hold more liquid water than the entire blue planet you are resting on right now. That is not a small thing. It also raises the question, in a relatively gentle way, the way it deserves to be raised as the room grows quiet. On Earth, wherever we find liquid water, we find life. In the deepest ocean trenches, in water heated by hydrothermal vents on the ocean floor, in ice-cold Antarctic lakes sealed from the atmosphere for millions of years. Life. Tenacious, inventive, opportunistic life. We have never found water anywhere on Earth that had no life in it whatsoever, even when we have looked very hard. Europa has a lot of water. Europa may also have hydrothermal vents on its ocean floor where the warm interior meets the liquid above. And Europa's ocean is not cut off from the outside entirely. The tidal flexing that keeps it liquid also churns the ice above it, and there are places on Europa's surface where the ice has cracked and shifted and may have allowed exchange between the ocean below and the space environment above. Does that mean there is life in Europa's ocean? No. We do not know. We have not looked. We have never sent anything into that ocean because we have not yet found the technological and logistical means to drill through many kilometers of ice and explore what is beneath. But the question is real and it is taken seriously, and the reason it is taken seriously is that the conditions we associate with life on Earth, liquid water, chemical gradients, energy, appear to exist in this small, smooth, Jupiter-orbiting moon. The Galileo mission gathered much of the evidence that convinced scientists the ocean was real. Magnetic measurements showed that Europa behaves like a body with a conducting layer. Salt water is an excellent conductor, not far below the surface. Juno has added to this picture, and a dedicated mission, Europa Clipper, is on its way to look even more closely. But for tonight, let Europa be what it is. A world with a secret. A small, smooth moon with an ocean larger than all of Earth's oceans combined, sealed under ice, orbiting in the radiation belts of Jupiter, in the dark and the cold. Whatever is or is not in that ocean, it is extraordinary. The fourth Galilean moon, Callisto, is the outermost, and in some ways it is the most ancient-looking of the four. Where Io is continuously remade and Europa is geologically active, Callisto is the opposite, a world that has barely changed in billions of years. It is heavily cratered. It does not appear to have experienced much geological resurfacing. It is, in the language of planetary science, a relic. A world that has sat largely undisturbed for the entire life of the solar system, accumulating its scars and wearing them all. There is something quietly beautiful about that, actually. Callisto as a record, a geological archive of the early solar system's bombardment phase, preserved because nothing has happened since to disturb it. Now, before we leave Jupiter's neighborhood entirely, there is one more name. One more moon in Jupiter's retinue that deserves a moment, because it keeps coming up in any honest accounting of the solar system's strange hierarchies. Ganymede. We mentioned it before, the largest moon in the solar system, larger than the planet Mercury. But let us sit with that for a moment in the way it deserves. Mercury is a planet. It is one of the 8 bodies that the International Astronomical Union has officially designated planets. One of the 8 bodies most people learn in school, one of the 8 bodies that for most of our history defined the boundary of what counted as a world. Mercury has a diameter of about 4,879 kilometers. Ganymede's diameter is about 5,268 kilometers. Ganymede is larger than an entire planet. It is not slightly larger, it is meaningfully, noticeably larger, by nearly 400 kilometers in diameter. And yet it is a moon. It orbits Jupiter, not the Sun, and so by the definitions we use, it is a moon rather than a planet. And it sits in a list that currently numbers 95 entries for Jupiter's moons alone. Ganymede is also the only moon in the solar system known to have its own magnetic field. All the other moons we have looked at, the Moon, Io, Europa, Titan, Triton, all of them, exist within the magnetic environment of the body they orbit, or in the absence of any real field. Ganymede generates its own. A proper magnetosphere, a bubble of magnetic influence surrounding this moon, like the planetary magnetic fields that surround Earth or Jupiter. No one else has one. Ganymede has one. We believe it arises from convection in a liquid iron core, the same basic mechanism that gives Earth its magnetic field, operating inside a moon. Ganymede, in other words, is a world that would be recognized as a world by almost any measure, except the specific one of what it orbits. This is the point where the conventional categories start to feel slightly insufficient. Not wrong, just insufficient for the actual diversity of what the solar system contains. And if that is becoming apparent in Jupiter's neighborhood, wait until we arrive at the next stop on our slow outward tour. The pale, ringed light grows stronger. Saturn. Approaching Saturn for the first time in any meaningful visual sense, whether through a telescope for the first time, or in a photograph, or in the extraordinary images returned by the Cassini spacecraft during its 13 years in orbit, there is a moment that almost everyone describes in a similar way. Disbelief. A sense that what you are looking at has been fabricated, that some trick of light or photography has added the rings, that a real object could not look like this. But it is real, entirely, astonishingly real. Saturn is the second largest planet in the solar system. It is about 9.5 times Earth's diameter, and like Jupiter, it is a gas giant, no solid surface to stand on, just atmosphere deepening into something that stops being atmosphere by any normal definition before you ever reach an interior. Its clouds are paler than Jupiter's, more cream and gold than the deep reds and oranges and browns of its neighbor, and from a distance it has a quieter, more serene quality. It spins fast. A day on Saturn is only about 10.5 hours, and like Jupiter, it is slightly flattened at the poles because of that rotation, a gentle squash that you can measure but that is hard to see in a single image. But none of that is what you are looking at when you look at Saturn. The rings. Saturn's rings are made primarily of water ice. Countless particles ranging from tiny grains like frost crystals to chunks the size of a house, all in orbit around the planet, all moving at speeds that keep them aloft, organized by the gravitational influence of Saturn and its moons into a structure that spans from about 6,700 kilometers above Saturn's cloud tops to about 80,000 kilometers out, and in some ring structures even further. The full ring system, including the more tenuous outer rings, extends to perhaps 280,000 kilometers, 280,000 kilometers across. That is about 70% of the distance from the Earth to the Moon. The rings of Saturn are not a thin disk in the way a vinyl record is a thin disk. They are not a feature. They are a structure on a scale that challenges the imagination. And then this, in places, they are only tens of meters thick.
Let that settle for a moment gently. 280,000 kilometers across, tens of meters thick. If you scaled Saturn's rings down to the size of a sheet of paper, standard office paper about 1/10 of a millimeter thick, the paper would need to be roughly the size of a large city to represent the rings in the right proportions.
A vast, translucent, sparkling sheet of ice particles, each one glinting as it catches the sun's light from a distance of nearly 9.5 astronomical units. The rings are young, geologically speaking. There is evidence that they formed relatively recently. In cosmic terms, perhaps in the last 100 million years or so, long after the dinosaurs appeared on Earth, let alone before. They might be the debris of a moon that wandered too close and was torn apart by Saturn's tidal forces, or the remnant of a collision. The exact origin is still being debated, but they will not last forever. The ice particles are slowly spiraling inward under the influence of Saturn's magnetic field and the solar wind, eventually to fall into Saturn's atmosphere. The rings, as glorious as they are, may be a temporary phenomenon. We happen to be alive at a moment when they are there to see, which is either a remarkable coincidence or simply a reminder that in 4.5 billion years, many things get their moment. Now, the rings are remarkable, and we could spend all night there, drifting through an ice field so vast and so thin, it is like flying through a snowflake the size of a city. But the rings are not the reason Saturn is the world record holder in this census of the solar system. The moons are. As of recent surveys, and the count, I want to emphasize, continues to rise, Saturn has more than 146 confirmed moons. 146. In surveys completed in 2023, Saturn passed Jupiter to become the planet with the most known moons in the solar system. This is likely to remain provisional in the sense that the number for both planets is still climbing as detection methods improve and fainter, smaller objects come within reach. But for now, Saturn leads, and Saturn leads by a significant margin. Think about what that means for the census. The 8 planets between them, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Number, by definition, 8. And 2 of those 8 planets, Jupiter with roughly 95 moons and Saturn with more than 146, together account for somewhere around 241 moons between them. More than 240 worlds orbiting just these 2 planets, against the 8 planets total. The solar system is not 8 worlds. It is several hundred worlds, and the 8 planets are the ones we named first, because they are the ones we could see. Most of Saturn's moons are small. Many are captured objects, icy bodies that strayed too close and were incorporated into Saturn's gravitational retinue, now in orbits that describe their captured nature. Tilted, elongated, sometimes retrograde. But not all of Saturn's moons are small, and some of them are among the most extraordinary places we know of anywhere. The largest of Saturn's moons is Titan. Titan is the second largest moon in the solar system. Only Ganymede is bigger, and like Ganymede, Titan is larger than the planet Mercury. It is a pattern worth noting. 3 of the solar system's moons, Ganymede, Titan, and Callisto, all comfortably exceed Mercury in size. The planet Mercury, one of the 8, is smaller than 3 of the moons in orbit around the outer solar system. But Titan is extraordinary in a way that goes well beyond its size. Titan is the only moon in the solar system with a thick atmosphere. Not a trace atmosphere, not a thin exosphere, not a barely there envelope of particles. a proper, substantial, continuous planet-like atmosphere, one that is in some ways denser than Earth's. The atmospheric pressure at Titan's surface is about 1.5 times the atmospheric pressure at sea level on Earth. You could stand on Titan's surface at roughly minus 179 degrees Celsius. You would not survive for very long, but you would not be crushed, and you would not float away. The pressure would feel approximately like standing a few meters underwater on Earth, heavy and present and real. The atmosphere is mostly nitrogen, which is interesting in itself. Earth's atmosphere is also mostly nitrogen, but where Earth's atmosphere has a critical fraction of oxygen and water vapor, Titan's has methane. And that methane, in Titan's cold, sets off a chemistry that does something astonishing. It rains. It rains methane on Titan. Liquid methane falls from Titan's orange haze clouds, hits the surface, fills craters and valleys, and channels the way water fills craters and valleys and channels on Earth, and flows downhill. And on Titan's surface, at the poles, there are lakes, seas, bodies of liquid methane and ethane sitting open at the surface, reflecting whatever light reaches Titan's cloud-shrouded ground, lapping against icy shores. This is the only other place in the solar system aside from Earth where stable liquid exists on the surface. Not ice, not vapor, liquid. Open liquid that you could, in principle, sail a boat across if the boat were built for methane at minus 179 degrees. The Cassini-Huygens mission gave us our most detailed picture of Titan. Cassini orbited Saturn for 13 years, from 2004 to 2017, and during that time it flew past Titan more than 100 times, using radar to peer through the opaque atmosphere and map the surface, finding dunes and plains and those extraordinary polar seas. Huygens was a probe that descended through Titan's atmosphere in January 2005, the most distant landing ever achieved at the time, drifting down on a parachute for more than 2 hours through the orange haze, returning images of a grey, pebbled, cold alien beach, river channels, rounded pebbles of water ice shaped by the flow of liquid methane, the way river stones on Earth are shaped by water. Huygens transmitted data for about 72 minutes after landing, 72 minutes from the surface of Titan, from a world where it rains hydrocarbons, and the air smells, in theory, of natural gas, and the lakes shimmer, not with water, but with something your chemistry teacher would have kept in a sealed container. There is something specifically strange about Titan that you can hold in mind as you settle deeper. The same basic atmospheric cycle that gives Earth rain and rivers and oceans, evaporation, cloud formation, precipitation, flow back to the sea, operates on Titan. Same cycle. Completely different chemistry. What Earth does with water, Titan does with methane. It is as if someone took the blueprint of Earth's hydrological system and substituted one molecule for another, and the whole thing still works. A different world running the same program. From Titan, we drift inward, closer to Saturn, to one of the most surprising objects in the entire solar system, given that it is only about 504 kilometers across. Enceladus. Enceladus is small. In the catalogue of Saturn's moons, it is one of many, its size not particularly remarkable. But what Enceladus does is remarkable, and what it does begins at the South Pole. At the South Pole of Enceladus, there are fractures in the ice, long parallel cracks roughly spaced, that the Cassini mission observed and mapped and ultimately named the tiger stripes, not because they look like tiger stripes in a photographic sense, but because they are striped, parallel, distinct. 4 main fractures, each roughly 130 kilometers long, each emanating intense heat relative to the surrounding surface. And from these fractures, Enceladus sprays water into space, not a trickle, not a slow seep, geysers. Geysers of water vapor and ice particles rising from the surface of this small moon, climbing hundreds of kilometers into space, escaping Enceladus's weak gravity and spreading out into Saturn's orbital environment. The Cassini spacecraft flew through these plumes and sampled them, tasting what Enceladus was throwing into space. And what it found was water. Salty water with complex organic molecules and silica particles that form when water contacts hot rock at high temperatures. The silica particles in particular are a strong chemical signal. They suggest that somewhere inside Enceladus, liquid water is interacting with a rocky, hot ocean floor. The same signal that would come from a hydrothermal vent. Enceladus has a subsurface ocean warmed by tidal heating from Saturn, kept liquid beneath its icy shell. And that ocean is not sealed as tightly as Europa's. Enceladus is actively venting it into space, and we have flown a spacecraft through the vent. We have tasted Enceladus's ocean from a distance of hundreds of kilometers, filtered through a scientific instrument on a spacecraft, but we have been chemically inside the ocean of Enceladus without ever needing to drill through the ice. The plumes do something else as well. The ice particles they eject travel outward from Enceladus and spread through a particular orbital region around Saturn, creating and continuously replenishing a faint, diffuse ring called the E-ring. The E-ring, one of Saturn's more tenuous outer rings, is made of Enceladus. It is made of the ocean of Enceladus, sprayed into space and organized into a ring by the dynamics of Saturn's gravity. A small world is building part of a planetary ring system from the inside out, using the water of its own hidden sea. When you look at Saturn's rings, you are, in a small but real way, looking at Enceladus. There are many other moons in Saturn's system. Mimas, whose enormous Herschel crater makes it look uncannily like a certain science fiction space station, a resemblance entirely coincidental, since Mimas was known long before that fictional station was designed, but striking enough to mention gently. Rhea, the second largest of Saturn's moons. Iapetus, one of the strangest-looking bodies in the solar system, with one hemisphere almost perfectly black and the other almost perfectly white, a two-tone world whose coloring is caused by the accumulation of dark material on its leading hemisphere as it sweeps through space. Dione and Tethys, icy moons with their own features and histories. Each one a world, each one with its own story to tell, if you had the time to listen to all of them in a single night. But the night is long, and we still have a long way to go. And there is a payoff to be stated, a ledger to be balanced before we move on. Jupiter's moons, approximately 95 confirmed. Saturn's moons, more than 146 confirmed. Together, roughly 241 moons orbiting just 2 planets. The total number of officially confirmed moons across the entire solar system, all 8 planets, stands at approximately 290 or more, and rising. Jupiter and Saturn together account for the overwhelming majority of that total. The other 6 planets, Mercury, Venus, Earth, Mars, Uranus, Neptune, share the remainder. 2 planets host more worlds in their gravitational embrace than the entire inventory of planets the solar system contains. The 8 planets are not the solar system, they are the solar system's headline act. The real solar system is this: an enormous, sprawling, intricate, still partially counted archipelago of moons and icy bodies and rocky fragments and frozen worlds, distributed from the hot neighborhood of the Sun out to distances we are still mapping, orbiting in configurations of extraordinary complexity, some of them, we think, harboring the conditions for liquid water, organic chemistry, and perhaps things stranger still. We travel outward, past Saturn's rings, the ice particles glinting as we leave them behind. We enter a region of the solar system that feels different in quality. Jupiter felt massive and imperial. Saturn felt ringed and world-rich and almost baroque in its complexity. What comes next feels more remote, more tilted away from the familiar, more like the outer edge of something that has a proper edge. Uranus. Uranus is the seventh planet from the Sun, orbiting at about 19 astronomical units, 19 times Earth's distance. Light from the Sun takes about 2.5 hours to reach it, and the planet receives only about a 27th of the solar energy that Earth does. It is cold, much colder than Saturn, much colder than anything in the inner solar system. The temperatures in its atmosphere drop to around -220 degrees Celsius, making it, alongside Neptune, one of the coldest places in the outer solar system. Uranus is an ice giant, a category distinct from the gas giants Jupiter and Saturn. Where Jupiter and Saturn are composed primarily of hydrogen and helium, with relatively small amounts of heavier elements, Uranus and Neptune have a different composition: more water, more ammonia, more methane ice. The ice in ice giant refers to these compounds in their high-pressure forms deep inside the planet, not to surface frost. Uranus has no surface. But what makes Uranus immediately, obviously singular, is its tilt. Most of the planets in the solar system are tilted slightly relative to their orbits around the Sun. Earth is tilted about 23 degrees, which gives us our seasons. Saturn is tilted about 27 degrees, Mars slightly more. These are gentle, sensible tilts for a planet that formed from a spinning disk of material and then settled into more or less upright stability. Uranus is tilted 98 degrees. It is essentially rolling on its side, where other planets spin like tops with their poles pointing more or less up and down. Uranus spins like a ball rolling across a table, with one pole pointing almost directly at the Sun for part of its orbit, and the other pole almost directly away. An orbit of Uranus takes about 84 Earth years, which means that one pole can experience continuous sunlight for about 42 years, while the other pole sits in darkness, and then they switch. This is not what any planet is supposed to do. The best explanation, and it is supported by quite a lot of evidence in how Uranus's moons are arranged and how they orbit, is that sometime in the early solar system Uranus was struck by something very large, perhaps a protoplanet, something the size of Earth or a bit bigger, and the impact was glancing but powerful enough to knock Uranus onto its side. And there it has stayed for billions of years, rolling around the Sun in its tilted way, its poles taking turns at the sunlight in a slow, strange 84-year cycle. If you were somehow standing in a hypothetical location above the solar system, looking down, you would see the other planets as spinning more or less upright tops in their orbits. And then Uranus rolling sideways like something that did not get the memo. Uranus has 28 known moons. This is a large number compared to Earth's 1 or Mars's 2, though small compared to Jupiter or Saturn. What is immediately distinctive about them is their names. While the moons of most other planets are named from Greek and Roman mythology, a tradition going back to the naming conventions of classical astronomy, the moons of Uranus are named from the works of William Shakespeare and Alexander Pope. This is not arbitrary. It is a convention that gives Uranus's moon system a particular literary character. The largest moons are Titania and Oberon, named for the fairy queen and king from A Midsummer Night's Dream. Then Umbriel and Ariel, named from The Rape of the Lock by Alexander Pope. Miranda from The Tempest. Caliban, Sycorax, Prospero, Setebos, also from Shakespeare. The ice giant orbiting in the dark of the outer solar system is accompanied by a court of characters from two of the most famous works of English literature, frozen in their names for as long as the planet holds them. Most of Uranus's moons are relatively small and have been studied primarily from a distance. No spacecraft has orbited Uranus, and the only close observations we have are from Voyager 2, which flew past in January 1986 and had only a brief encounter to gather what data it could before the geometry of the flyby took it onwards. The images from that encounter are everything we have in terms of close observation, and they revealed, among other things, something about Miranda that warranted more than a passing mention. Miranda is the smallest of the 5 major Uranian moons, at about 472 kilometers across. It is not large, but its surface is one of the strangest in the solar system. Rather than the uniform cratered look of many small moons, or the smooth resurfacing of something geologically active, Miranda's surface looks like it has been assembled from mismatched pieces. Ridges and valleys and canyons that seem to belong to different geological histories placed next to each other with jarring abruptness. There are regions that look heavily cratered and ancient, right next to regions that look young and disturbed. Scientists have proposed various explanations. Perhaps Miranda was broken apart by a collision and reassembled in a slightly scrambled way, or perhaps it has had an unusual tidal heating history. But the truth is that Miranda is still something of a geological puzzle. What is not a puzzle is Verona Rupes. Verona Rupes is a cliff on Miranda, and it is, as best we can measure, the tallest known cliff in the solar system. It is approximately 20 kilometers high. For context, the tallest cliff on Earth, in terms of sheer vertical drop, is a few kilometers at most. Verona Rupes is somewhere between 4 and 10 times taller than the tallest terrestrial cliff, standing on a moon barely 472 kilometers across, discovered in images from a single flyby by a spacecraft that had already been traveling for 9 years by the time it arrived. If you fell from the top of Verona Rupes, in Miranda's weak gravity, you would fall for somewhere around 10 minutes before reaching the bottom. 10 minutes. That is enough time to watch the landscape spread out below you, to see the curvature of this tiny moon, to watch the stars wheel slowly overhead as the cliff face passes in slow motion beside you. Long enough to think many thoughts, whatever they might be, on the way down. There is something quietly wonderful about the existence of Verona Rupes, a cliff 20 kilometers tall on a moon of Uranus named after the city in a Shakespeare play, discovered by a spacecraft that was launched in 1977, standing in the dark of the outer solar system where the Sun is only a bright star among many, and the temperature has never, not once, in the planet's entire history, been above deeply cold. The solar system makes things on scales that require the imagination to stretch, and then places them where almost nothing will ever see them or know they are there. Verona Rupes has been standing since whatever event created it. Probably billions of years ago, no one knew it existed until 1986, and even now, only a handful of spacecraft images document its existence. It is patient. Everything out here is patient. We drift onward. Uranus falls behind, tilted and quiet, its Shakespeare moons in their orbits, Miranda's cliff catching no particular light in the long, cold dark. We keep going, outward, away from the Sun, into the region where what we think of as the solar system begins to blur into something less familiar, something that requires more imagination to picture even with the help of science. But not yet. There is still Neptune. And Neptune is, in almost every way, an astonishment. It sits nearly 30 astronomical units from the Sun, so far that sunlight, which reaches Earth in about 8 minutes, takes roughly 4 hours to arrive here. The Sun itself, seen from Neptune, is not the warm disk you know. It is a very bright star, beautiful in its way, cold in every way. If you were standing somewhere near Neptune, you would need instruments to feel any warmth from it at all. And yet, for all that distance and cold, Neptune is not a quiet place. Not remotely. Neptune is the windiest planet in the solar system. Not the largest, not the most massive, the windiest. Its atmosphere churns at speeds that reach around 2,000 kilometers per hour. 2,000. To give that some shape, the strongest hurricanes ever measured on Earth carry winds of perhaps 300 kilometers per hour, which is enough to tear buildings from their foundations, lift rooftops, bend steel. Neptune does more than 6 times that, routinely. As a matter of atmospheric habit, we don't fully understand why. Neptune receives very little energy from the Sun at that distance, which means that energy should not be able to drive winds of that ferocity. There simply isn't enough sunlight arriving to explain it. The current thinking is that Neptune has an internal heat source, some remnant warmth from the planet's formation, that it radiates outward through the atmosphere, and this internal warmth somehow interacts with the cold exterior in a way that generates extraordinary wind. But the honest answer is that the mechanism isn't entirely understood. Neptune makes its weather by rules we haven't quite figured out yet, which feels, honestly, fitting. The outer solar system seems to specialize in behaving in ways that defy comfortable expectation. Neptune is an ice giant like Uranus, though calling it an ice giant is a little misleading because the ices inside it are nothing like the ice in your freezer. They are hot, pressurized exotic phases of water and ammonia and methane compressed into a dense slurry beneath layers of gas. The planet is smaller than Uranus in volume, but actually more massive, denser, as though more material got packed into a slightly smaller space. It is a deep, rich, vivid blue, a true blue unlike Uranus's pale, washed-out teal, and that color comes from methane in the upper atmosphere, absorbing red light and reflecting blue back into space. If you could see Neptune with your naked eye, which you cannot quite manage from Earth, it would be genuinely, strikingly beautiful. A blue gem at the edge of the planetary neighborhood. And Neptune has moons. 16 known so far. A respectable collection for a world so far from the Sun. Most of them are small, irregular, tumbling in orbits that suggest they were captured from the Kuiper Belt at some point in the distant past, rather than forming in place alongside their planet. Most of them have names drawn from Greek and Roman mythology of the sea. Nereid, Proteus, Larissa, Despina, and others. A quiet company of small, frozen worlds orbiting in the cold. But the one that matters most, the one that stops you, is Triton. Triton is Neptune's largest moon, and Triton is wrong. Not wrong in a poetic sense, but wrong in the literal sense that its existence shouldn't work the way it does. Every other large moon in the solar system orbits its planet in the same direction the planet rotates. That is the expected pattern. It is the pattern you get when a moon forms from the same cloud of material that formed the planet, spinning together in the same original motion. Io orbits Jupiter in the same direction Jupiter spins. Titan orbits Saturn the same way. All of the Galilean moons, all of Saturn's major moons, most large moons everywhere, they orbit forward, as it were, in the direction of rotation. It is the solar system's default. Triton orbits Neptune backwards. It is the only large moon in the solar system with a retrograde orbit, meaning it moves around Neptune in the opposite direction to Neptune's own rotation. And there is really only one plausible explanation for that. Triton did not form here. Triton formed somewhere else, out in the Kuiper Belt, drifting in its original orbit, and at some point in the deep past it was captured by Neptune's gravity and pulled into this backwards orbit, a world from one part of the solar system claimed by a planet in another. The capture itself would have been dramatic, presumably. A large body encountering a planet's gravity, shedding enough energy somehow to be caught rather than flung away, settling over time into the stable, backwards orbit it holds today. The details of exactly how Triton was captured are still debated, but the backwards orbit is evidence that is difficult to argue with. And there is a consequence to orbiting backwards. A moon that orbits against its planet's rotation creates a kind of gravitational drag, a slow, patient, tidal friction between the moon and the planet. And that friction is gradually stealing energy from Triton's orbit, pulling it slightly closer to Neptune with every pass. It is the same process at work on Phobos, circling Mars. It is slow, deeply slow, measured on timescales beyond human intuition, but it is real, and it is happening. At some point in the future, estimates vary, but the order of magnitude is many millions of years. Triton will drift close enough to Neptune that the planet's tidal forces will tear it apart, shredding it into a ring system, or it will spiral all the way in and impact the planet's atmosphere. Triton is on borrowed time. Its orbit is a clock running down, but for now it is still there. Still circling Neptune in the wrong direction, at a distance of just over 300,000 kilometers from the cloud tops. Triton was visited by only one spacecraft ever, Voyager 2, which passed Neptune and Triton in August of 1989. It is still the only close look we have managed, and what Voyager 2 found in those hours of flyby, within those few irreplaceable hours, was extraordinary. Triton is cold, genuinely, profoundly cold. Its surface temperature is around negative 235 degrees Celsius, which makes it one of the coldest measured surfaces anywhere in the solar system. Not the coldest, but close. At that temperature, nitrogen, the same gas that makes up most of the air you are breathing right now, is frozen solid on the ground, a pale pinkish frost covering large areas of the surface, mixed with frozen methane and carbon dioxide. The terrain is strange and varied. There are smooth plains, ridged and buckled terrain that has been described as looking like the skin of a cantaloupe, and features that suggest the surface has been geologically active, reshaped and remelted at various points in its history. And then there are the geysers. Voyager 2 spotted dark streaks on Triton's surface, and after analysis the conclusion was that they were caused by geysers. Not water geysers, nitrogen geysers. The Sun, even at Neptune's vast distance, even as just a bright star, provides just enough warmth to sublimate frozen nitrogen beneath a thin, transparent layer of ice. The nitrogen turns to gas, pressure builds, and it erupts upward through the ice in dark plumes that rise several kilometers into Triton's thin atmosphere before being carried downwind, painting those dark streaks across the pale surface. Geysers of nitrogen on a frozen captured moon orbiting backwards around the windiest planet in the solar system, at the edge of what we conventionally call the planetary neighborhood. The solar system keeps adding rooms when you think you've counted them all. Triton is, in the end, probably not so different from many of the objects we are about to meet in the Kuiper Belt. It is, in a sense, a Kuiper Belt object that wandered too close to a planet and stayed. A representative of an entire frozen world beyond the planets currently residing among the planets. A preview of what comes next, and what comes next is the Kuiper Belt. Let your mind go quiet for a moment. Picture the planetary system as you learned it, the Sun at the center, then Mercury, Venus, Earth, Mars, a gap with the asteroid belt, then Jupiter, Saturn, Uranus, Neptune. 8 planets in their orbits. It is a tidy picture. A clear, comprehensible map. Now imagine that beyond Neptune, where you might expect the solar system to simply end or thin out and stop, instead you encounter a new region, vast and filled with bodies, stretching from around 30 astronomical units from the Sun out to perhaps 50 or so, a belt like the asteroid belt, but far larger and far more massive. Hundreds of thousands of icy bodies that we know about, and certainly many more that we haven't found yet, ranging from small chunks of rock and ice to bodies large enough to be rounded by their own gravity, large enough by the criteria that matter to be considered worlds in their own right. That is the Kuiper Belt, and it is not empty, not even close. The asteroid belt, as we noted earlier in this journey, has a total mass that is only about 3% of the Moon's. It is overwhelmingly empty space. The Kuiper Belt is different. It is significantly more massive than the asteroid belt, though still small by planetary standards. And it is populated by objects that are in some ways more interesting than most of the asteroid belt's residents. Frozen, preserved, ancient, ranging from simple rocks to elaborate worlds with their own moons, and even, in at least one case, their own rings. This is also, for historical reasons, the most contentious region of the solar system, because this is where Pluto lives. Pluto was discovered in 1930 by a young American astronomer named Clyde Tombaugh at the Lowell Observatory in Arizona. For 76 years, it was the 9th planet. School children learned its name. Textbooks depicted it. A Disney character was named after it the same year it was found. It occupied a comfortable and unquestioned place in the solar system's mental map. And then, in 2006, the International Astronomical Union is the professional body that handles such definitions, voted on a formal definition of what a planet actually is. The definition had 3 conditions. A planet must orbit the Sun, must be massive enough for gravity to pull it into a roughly spherical shape, and must have cleared the neighborhood of its orbit of other bodies. Pluto met the first 2 conditions, but the third, clearing its neighborhood, it failed. The Kuiper Belt is full of other bodies, and Pluto has not gravitationally dominated its orbital region the way Jupiter or Saturn or even Earth clearly has. So Pluto was reclassified. It became a dwarf planet, a new category that included similarly sized rounded bodies that don't meet the full planetary definition. It was a demotion that generated headlines, public debate, and genuinely strong feelings, which tells you something about how deeply humans invest in the names and categories of things they have never seen and never will see in person. But here is the thing, here is what is actually interesting about the Pluto story, the part that gets less attention than the demotion itself. The reason the IAU was forced to create a new definition was not really because of Pluto. It was because of something else, something that forced the issue, and that something was Eris. Eris was discovered in 2005, and when astronomers measured it carefully, they found that Eris is actually more massive than Pluto. Not just a similar size, more massive. If Pluto were a planet, then Eris would have to be a planet too. And at the time of Eris's discovery, there were already hints that the Kuiper Belt might contain many more Pluto-sized or near Pluto-sized objects. If the definition of planet was simply rounded body orbiting the Sun, the solar system might turn out to have not 9 planets but dozens, or perhaps over 100. The question of how many planets there are would become unanswerable in a satisfying way. And so the IAU decided to draw a line. Pluto and Eris and similar objects became dwarf planets, and the solar system officially had 8 planets again. Eris received its own moon in this story. It is called Dysnomia, named after the goddess of lawlessness, a companion perhaps to Eris, the goddess of discord. Eris and Dysnomia orbit each other out in the cold, roughly 96 astronomical units from the Sun at their most distant, nearly twice as far from the Sun as Pluto. Eris is a small frozen world, its surface bright with methane ice, sitting in the outer reaches of what is called the scattered disk, a population of objects with highly elliptical orbits that reach far beyond the main Kuiper Belt, more massive than Pluto and farther out and quieter. The world that changed the definition of everything. But let us stay a little longer in the Kuiper Belt proper, because Pluto deserves more than a demotion story. Pluto is genuinely unexpectedly extraordinary. Before 2015, we had no close images of it, none. For 85 years after its discovery, Pluto was a smudge, a point of light in telescope images, its surface unmappable, its nature largely guessed at. We knew it was small, smaller than Earth's moon. We knew it had moons. We knew it was cold and icy and distant, but the details were hidden. Then New Horizons arrived. New Horizons was launched in January 2006, the same year, coincidentally, that Pluto was demoted, and it flew past Pluto in July 2015, after 9.5 years of travel. And what it found in those hours of closest approach overturned almost every expectation anyone had been holding. Pluto has a heart. Not metaphorically, literally. There is a vast, pale, nitrogen ice plain on its surface, shaped from above, unmistakably, like a heart. It is called Tombor Regio, named after Clyde Tombaugh, the astronomer who discovered Pluto. It is roughly the size of Texas and Oklahoma combined. It is bright, strikingly bright, because it is covered in freshly formed nitrogen ice that has been moved around geologically, cycled and redeposited in ways that suggest the interior of Pluto is still warmer than its surface. Pluto, tiny and frozen and billions of kilometers from the Sun, appears to have some form of geological activity, a dwarf planet with a heartbeat. The mountains on Pluto reach up to about 3.5 kilometers high, and they are made of water ice. Not frozen nitrogen. That is too soft to stand tall. These are genuine mountain ranges of water ice, protruding through the nitrogen plains, ancient and still. The Tombor Regio plain itself appears to be young by geological standards, its smooth surface suggesting it has been reshaped within the last few 100 million years, which is recent in solar system time. And Pluto has moons, 5 of them. The largest, Charon, is so large relative to Pluto, just over half Pluto's diameter, that the two bodies do not actually orbit each other in the conventional sense of a planet and its moon. Normally, a moon orbits a point very close to the center of its planet. Earth's moon, for example, orbits a point that is deep inside the Earth. But Charon is massive enough that the point the two orbit, the barycenter, the center of mass of the Pluto-Charon system, actually lies outside Pluto itself, in the empty space between them. They orbit a point in empty space, which makes Pluto and Charon, strictly speaking, a double world. 2 worlds in a gravitational partnership, rotating around nothing, far from the Sun and far from everything they originally formed near. The other 4 moons of Pluto, Styx, Nix, Kerberos, and Hydra, are much smaller, tumbling in their orbits in ways that suggest they may have originated from a collision early in the system's history, the debris eventually coalescing into the small, irregular shapes they have today. And then there is Haumea. Haumea is one of the 5 officially recognized dwarf planets, and it is, in physical terms, probably the strangest shaped world in the solar system. Most worlds that are large enough for gravity to matter are pulled into roughly spherical shapes. Gravity is democratic. It pulls equally in all directions, and given enough mass and enough time, it rounds things out. But Haumea is spinning, extremely fast. Its day, one complete rotation, takes only about 4 hours. And at that speed, the centrifugal effect of the spin is strong enough to overcome the rounding tendency of gravity. Haumea is not a sphere. It is an ellipsoid, elongated, squashed, egg-shaped. If you were to see Haumea from above, it would look less like a small planet and more like a slightly squashed melon, or perhaps an American football that gravity is losing an argument with. And as if that were not enough, Haumea has rings. Small rings discovered in 2017, making it one of only a few non-planetary bodies in the solar system known to have a ring system. It also has 2 moons, Hiiaka and Namaka, orbiting this fast-spinning, egg-shaped world in the outer solar system. Everything about Haumea feels like the solar system decided to run an experiment in how strange it could make a single object. Beyond Haumea and Eris and Pluto, the Kuiper Belt has other inhabitants worth knowing by name, even briefly. Makemake, another officially recognized dwarf planet, roughly two-thirds the size of Pluto, reddish in color, its surface covered in frozen methane, found to have at least one small moon. Its name comes from the mythology of the Rapa Nui people of Easter Island, the creators. It is a quiet world, largely unexplored, orbiting in the cold. Quaoar, a world about half Pluto's diameter, named after a creation deity of the Tongva people of California. Quaoar has its own moon, Weiwot, and in 2022 astronomers discovered that it too has a ring that exists at a distance where rings shouldn't, according to the conventional models, because it lies beyond what is called the Roche limit, the zone where tidal forces would prevent ring material from clumping together and forming a moon. Quaoar's ring should have become a moon by now. It hasn't. It is another place where the solar system is doing something the textbooks haven't fully accounted for yet. Arrokoth is sometimes called the anti-Pluto, not because it is opposite Pluto in character, but because its orbit is almost a mirror image of Pluto's, reaching similar distances, tilted at a similar angle, as if the two were paired. Arrokoth has a large moon called Vanth, and its surface appears to be coated in water ice and possibly ammonia. It orbits in the cold, doing its anti-Pluto thing, largely unvisited and unobserved. And Gonggong, named after a Chinese water god, a world roughly comparable in size to Sedna, with a reddish surface suggesting complex organic molecules, and a moon called Xiangliu. It has an orbit that takes it out to extraordinary distances, over 100 astronomical units from the Sun at its farthest point, a red, frozen, distant world with its own companion. These names, Makemake, Quaoar, Arrokoth, Gonggong, they are not household words. Most people have never heard them, but they are real places. They are real worlds, each rounded by gravity, each carrying their own histories of formation and collision and freezing, each orbiting the same star you orbit, each catching the same faint, cold starlight that barely reaches this far. There may be dozens more like them still unnamed in the dark, too distant or too faint for current telescopes to have found yet. The current estimate is that there could be dozens to over 100 dwarf planet candidates in the Kuiper Belt and the regions beyond waiting to be found. The census is not finished, the solar system is not fully counted, but before we leave the Kuiper Belt entirely, there is one more world that deserves its moment. In January 2019, New Horizons, the same spacecraft that visited Pluto in 2015, flew past a small body called Arrokoth. The name comes from the Powhatan and Algonquian peoples, meaning sky, and Arrokoth has the distinction of being the most distant object ever explored up close by a spacecraft. It sits about 44 astronomical units from the Sun. No human-made object had ever gone so far and looked so carefully at anything before that encounter. What New Horizons found was a contact binary. Two lobes, roughly reddish and smooth, fused gently together into a shape that was immediately and universally described as a snowman. Two rounded bodies touching merged at their contact point, probably brought together by the slow, gentle collision of two objects that had been drifting toward each other for a very long time. A cosmic, slow-motion tap. Each lobe is thought to have formed from smaller particles slowly clumping together in the original solar nebula, before being incorporated into this two-part, frozen world. Arrokoth is pristine. It is cold enough and far enough from everything that it has barely been altered since the early days of the solar system. Looking at Arrokoth is, in a sense, like looking at raw material, like seeing the building blocks from which worlds grow, preserved in the cold for 4.5 billion years. a snowman at the edge of the known, made of the dust that the sun did not need. And now we go farther still. Beyond the Kuiper Belt, beyond even the scattered disk where Eris wanders, there are objects whose orbits are so extreme that they barely seem to belong to the solar system at all. Objects that spend the vast majority of their time in depths of cold and dark so profound that we can barely imagine them, drifting so slowly at their far points that they seem almost stationary against the stars before falling gradually back in toward the sun for a brief, relatively close passage and then receding again for thousands of years. Sedna is the most striking known example. Sedna was discovered in 2003, and it was immediately clear that it was unusual. Its orbit is extraordinarily elongated, a long, drawn-out ellipse that takes it from roughly 76 astronomical units at its closest to the Sun, out to perhaps 900 astronomical units or more at its farthest, and one full orbit, 1 year on Sedna, takes approximately 11,000 years. 11,000 years. To put that in a framework that might help it land, 11,000 years ago, human beings were in the early stages of developing agriculture. The first cities were thousands of years away. Writing had not been invented. The entire span of recorded human history, all of it, is shorter than one Sedna year. Sedna is currently at a relatively close point in its orbit, which is why we found it. At its farthest, it retreats so far from the Sun that it would be essentially undetectable with current technology. We are, in a sense, lucky to have found it at all. And that raises a question that astronomers have been turning over ever since the discovery. How did Sedna end up with an orbit like that? Its orbit is so unusual that it doesn't fit neatly into any of the standard models of how the Kuiper Belt formed or how objects get scattered to extreme distances. Some researchers have suggested that Sedna's peculiar orbit might be evidence that something, another large body, perhaps a yet undiscovered planet, has been perturbing the outer solar system. That question is open. No such planet has been confirmed, but Sedna's orbit remains a puzzle, and puzzles in astronomy tend to eventually lead somewhere. Sedna is red, very red, one of the reddest objects known in the solar system. That reddish color is thought to come from the same kind of complex organic molecules that color many Kuiper Belt and scattered disk objects. Simple molecules transformed by billions of years of bombardment with cosmic radiation into more complex, reddish compounds. Sedna's surface is a record of chemistry and time painted red by the deep darkness. And then, beyond even Sedna, we reach the place where the solar system stops being something you can point to and starts being something you can only theorize about, the Oort Cloud. The Oort Cloud has never been directly observed. Let that sit for a moment. Everything we have talked about up to this point, the planets, the moons, the Kuiper Belt objects, Sedna, all of these have been detected, imaged, studied, their orbits measured. But the Oort Cloud is a theoretical object, a vast, hypothesized spherical shell of icy bodies thought to surround the entire solar system at enormous distances, from roughly 2,000 astronomical units out to perhaps 100,000 astronomical units, maybe further, 100,000 times the distance from the Earth to the Sun. The reason astronomers are confident it exists, despite never having seen it, is that long-period comets, comets with orbital periods of hundreds or thousands of years, come from somewhere. They fall inward from the outer solar system on steeply inclined orbits that suggest they originated very far away, in a roughly spherical distribution around the Sun, rather than in the flattened disk of the Kuiper Belt. Something is disturbing them, a passing star, the gravity of the galaxy itself, perhaps other forces, and sending them on long journeys inward. The Oort Cloud is the most plausible explanation for where they come from. It is inferred from the comets it occasionally, reluctantly, releases. If the Oort Cloud exists as theorized, it is immense beyond easy description. 100,000 astronomical units is almost 2 light-years, not quite halfway to the nearest star, Proxima Centauri, but a substantial fraction of the way. The solar system, if you include the Oort Cloud, does not end at Neptune. It does not end at the Kuiper Belt. It extends outward into a volume of space so enormous that the entire visible named planetary system, everything we have been touring tonight, from Mercury to Pluto to Arrokoth to Sedna, sits in a tiny glowing knot at the center of something almost unthinkably larger. And somewhere in all of that, billions of icy bodies are drifting in the cold and the dark, barely held by the sun's gravity, occasionally nudged by something, sometimes beginning the long fall inward to briefly become comets, streaking through the inner solar system, briefly bright, and then receding again for millennia. There is a boundary we can speak of with more certainty, though. The heliopause. This is the edge where the solar wind, the continuous stream of charged particles flowing outward from the sun, finally becomes too weak to hold back the wind of the interstellar medium, the diffuse matter filling the space between stars. At the heliopause, the sun's influence in that particular form ends. Everything within it is, in a physical sense, inside the sun's bubble. Everything beyond it is interstellar space. And that boundary was crossed for the first time by any human-made object in 2012. Voyager 1 was launched in September 1977. It has been flying without any significant fuel use for decades, coasting on the momentum of its original launch and the gravitational assists it received from Jupiter and Saturn ever since. It flew past Jupiter in 1979, past Saturn in 1980, and then it kept going, past Uranus's orbit, past Neptune's orbit, into the Kuiper Belt and through it, past the scattered disk. For 35 years it flew outward, and in August 2012, the instruments on Voyager 1 recorded a change in the environment around the spacecraft. The solar wind, which had been present in measurable form throughout the entire journey, suddenly dropped away. The magnetic field shifted. The levels of cosmic rays from interstellar space, which the solar wind had been partially blocking, increased sharply. Voyager 1 had crossed the heliopause. It was in interstellar space. The spacecraft is now more than 22 billion kilometers from the Sun. The radio signals it sends back to Earth, traveling at the speed of light, take more than 20 hours to arrive. When mission controllers at NASA send a command to Voyager 1, they wait nearly 2 days for it to arrive and for any confirmation to come back. And Voyager 1 is still not out of the solar system. The Oort Cloud, if it exists, extends far, far beyond where Voyager 1 is now. By one estimate, it could take the spacecraft another 300 years to reach the inner edge of the Oort Cloud, and perhaps 30,000 years to cross through it entirely. 30,000 years, the entirety of all human civilization, twice over just to cross the Sun's outermost hypothetical neighborhood. That is how large this is. That is what you are living inside, and here we are at the edge of the map. Not the real edge. The real edge is out there somewhere, tens of thousands of astronomical units away, the last dispersed wisps of the Oort Cloud, blurring gradually into interstellar space, indistinguishable in the end from the general medium between stars, but the edge of what we have visited, what we have imaged, what we have named. Beyond this, the solar system becomes something theorized and inferred rather than observed, a matter of inference from comets and gravity and the math of orbital dynamics. We started tonight at the Sun, at the thing that contains 99.86% of everything. The enormous, patient, ancient star that was already middle-aged before Earth formed, and we moved outward, step by step, world by world, through the 8 planets and their retinue of moons, through the asteroid belt with its surprising emptiness, out to Jupiter with its 95 moons and its Galilean worlds of fire and hidden oceans, to Saturn with its 146 and its methane seas and its geysers and its extraordinary rings, to Uranus tilted on its side and Miranda with its impossible cliff. And now, here, past Neptune and Triton and Pluto, and all those other round, frozen named worlds drifting in the Kuiper Belt, to Arrokoth and Sedna, and the theoretical immensity of the Oort Cloud. And the through line, the thing this tour was always building toward, is a simple one, but it is worth saying clearly now that we are at the end of it. The solar system does not contain 8 worlds. The number 8 is a historical artifact, a clean line drawn through a population that is anything but small and clean. At last count, there are approximately 290 confirmed moons orbiting various bodies in this system, and that count keeps rising as surveys improve and as the outer solar system reveals more of itself. Jupiter alone hosts roughly 95. Saturn, which recently overtook Jupiter to become the moon-richest planet, hosts over 146. Those 2 planets together account for something in the range of 240 moons, which already more than outnumbers the 8 official planets. Add the moons of the other 6 planets, and the total sits near 300. 300 worlds, most of them moons, most of them icy, most of them in the cold outer system, largely unvisited and almost entirely unknown in any detail. Every single one of them a real place. Every single one of them a surface, a history, a set of processes operating without any witness, geysers erupting on Triton with no one to see them. The methane tide, such as it is on Titan, shifting slightly with the seasons. Europa's ice shifting and cracking over the hidden ocean beneath. Eo's volcanoes erupting continuously, as they have been erupting for as long as Io has orbited Jupiter, whether or not any telescope was pointed at it. And then there are the dwarf planets. Officially 5, but almost certainly many more, perhaps dozens, perhaps over 100, hidden in the dark of the Kuiper Belt and the scattered disk, too small or too distant to have been found yet. Each of them potentially a world like Pluto, more complex, more geological, more strange than anyone expected, until New Horizons arrived and showed us what a dwarf planet could be.
And the Kuiper Belt itself, and the Oort Cloud beyond it, and the numberless comets waiting in the cold for a gravitational nudge to send them falling sunward for the first and only time.
The solar system is not 8 planets with some rocks and ice thrown in. It is an immense, complex, still being counted wilderness, and the 8 planets are a small, bright clearing in the center of it. The moons outnumber the planets by a factor of more than 30. The icy bodies of the Kuiper Belt and beyond may outnumber the confirmed moons, and the mass, the actual physical substance of the system, is so overwhelmingly concentrated in the Sun that everything else, all of it, combined, everything we have visited tonight, is less than a fraction of a % of the whole. We are debris. Beautiful, extraordinarily varied, sometimes geologically active, sometimes ocean-bearing, sometimes moon-bearing debris. Everything you know and everything you are exists in the rounding error at the edge of a star's budget. That could be a humbling thought, and perhaps it is, but I find it something else too. Sit with it a little differently and it becomes something closer to wonder, because even in that rounding error, look at what assembled itself. Look at what the leftover matter managed to become. A planet where liquid water collects in oceans and rivers and rain clouds in living cells. A moon where active volcanoes erupt continuously into the vacuum, painting the surface in sulfur yellows and oranges that can be seen from millions of kilometers away. Another moon where liquid methane falls as rain and collects in lakes and seas, where a probe we built and landed in 2005 sat on the surface and measured the alien wind. Another where a subsurface ocean sits beneath kilometres of ice, possibly larger than all Earth's oceans, possibly warm enough near the rocky bottom to support chemistry we would call interesting, in the most specific and careful sense of the word. A dwarf planet with a heart drawn in nitrogen ice and mountains built of frozen water. A contact binary snowman drifting at the furthest reach of our exploration, unchanged since the solar system was young. A captured moon orbiting backwards, its geysers dark against the pale, frozen nitrogen surface, slowly spiraling toward the fate of all things that spend their time too close to something much larger than themselves. A cliff 20 kilometers tall, standing in the outer dark, named for a city in a play, patient and cold and enormous and wonderful, with no one to fall from it. These are the things that fall into orbit around a single middle-aged star. These are the things that assemble themselves from the surplus. From the matter the sun did not need, from the dust and gas that swirled in the outer regions of a protoplanetary disk 4.5 billion years ago and found, through gravity and collision and time, arrangements that became worlds. The census is not finished. Astronomers are still finding moons, still cataloguing Kuiper Belt objects, still mapping the orbits of bodies so distant that their orbital periods are longer than the entire history of human civilization. The number of confirmed moons will be different by the time this reaches you than it was when the research for this was gathered. Some new discovery, quiet and technical, will have added another world to the count. The solar system's population is still being taken. And somewhere out there, in all of that dark, Voyager 1 is still flying. A machine built in the 1970s, smaller than a car, carrying a golden record with sounds of Earth pressed into its surface, crossing the boundary of the heliosphere and moving slowly through the interstellar medium. Its nuclear power source is fading. There will come a point, not so many years from now, when the science instruments go dark and it becomes simply a moving object, a piece of metal in the dark. But it is out there now, still transmitting, still measuring the environment it finds itself in. A message in a bottle thrown into an ocean so large that even light takes years to cross the nearest neighborhoods. You, wherever you are tonight, in a bed, on a couch, on a train, or somewhere I haven't thought of, you are on one of these worlds. Specifically, you are on the third planet from the star, on the one that got lucky with liquid water and an atmosphere and that particular arrangement of chemistry that somehow became self-aware and curious and eventually started building things that could fly past other worlds and send pictures home. You are made of the same material as all of it, the same carbon, the same oxygen, the same silicon and iron and nitrogen, the same atoms that are frozen into Pluto's heart are in your bones and your breath. The same water that hides beneath Europa's ice is what your body is mostly made of. The same hydrogen that burns in the sun was the raw material from which everything, including you, was assembled. You are not separate from the solar system. You are a piece of it, a piece that somehow got complicated enough to be here in the dark, listening to someone describe the rest. The count of worlds will keep rising. New missions will reach new targets. Jupiter's moons, Uranus's strange tilted system, the Kuiper Belt's frozen population. New telescopes will find fainter objects at greater distances. The map will keep expanding, but the shape of the story beyond the one this tour has been tracing will stay the same. The solar system is vastly larger than the 8-planet model suggests, filled with worlds most people have never heard of. And the further out you travel, the stranger and more populous it becomes, until it fades into a frontier that has no clear edge, only a gradual loosening, like the last light before true dark. We started tonight at the sun, at 99.86% of everything, enormous and patient and ancient. We moved outward through the inner worlds, the asteroid belt, the gas giants, and their extraordinary moons, the ice giants, and their captured companions, the dwarf planets, and their double orbits, the frozen snowmen of the Kuiper Belt, and out to Sedna and the theorized immensity of the Oort Cloud. We covered distance that would take the fastest spacecraft decades to cross. We visited places where the temperature has never been above deeply cold, where days are measured in human lifetimes, where 1 year takes 11,000 years. And then we came back. You are still here. Wherever you were when we began, in that bed, under that blanket, lamp perhaps still softly on, the particular quiet of whatever time it is in your corner of the world, you are still there, and the solar system is still out there, doing exactly what it was doing before you started listening. Jupiter's moons are in their orbits. Titan's methane clouds are moving slowly in the thick orange haze. Enceladus is spraying its ocean into space and feeding the E-ring particle by patient particle. Triton is circling Neptune the wrong way. Pluto's heart is bright and pale in the dark. And you, somewhere in all of that, one small warm being on one small warm world. Drift now into whatever sleep is coming. Thank you for traveling with me tonight, all the way out to the last frozen rock. If this slow journey through the solar system gave you something soft or strange to carry into sleep, I would love to know where you are in the world tonight and what time it is in your corner of the dark. Leave that in the comments if you feel like it when you wake. And if you'd like more nights like this one, a gentle like and a subscribe means a great deal to a small channel like this one. Small creators really do rely on your support to keep these journeys going. Until next time, good night from up here in orbit. I'll keep watch while you drift.